The world doesn't always announce when something extraordinary is about to happen. Sometimes the signs are scattered across the sky, hidden in data streams, and buried deep within the ground. But in September 2025, those signs began to converge, loudly, violently, and all at once. Within a single week, the Earth trembled, the sky ignited, and an object from beyond our solar system edged closer to the Sun than any interstellar traveler in recorded history. For scientists, it was a week of coincidence. For everyone else paying attention, it felt like the universe itself was trying to send a message. It began with the Sun. After nearly a decade of quiet slumber, our star suddenly stirred with renewed intensity. Massive magnetic fields twisted and snapped across its surface, releasing waves of charged particles that raced toward Earth at hundreds of kilometers per second. The result, a G3 geomagnetic storm, one of the strongest of the solar cycle, powerful enough to light up the night skies in colors that reached far beyond the Arctic Circle. For 2 nights, the upper atmosphere danced in silent waves of green and crimson, like some ethereal warning signal painted across the heavens. Then, 3 days later, the planet answered back. Off the coast of Russia's Kamchatka Peninsula, the seafloor shuddered violently as a magnitude 7.8 earthquake ripped through one of the most volatile fault lines on Earth. It was the second major quake to strike the same region in less than 2 months, an aftershock that felt more like an opening act for something far greater. And hovering at the edge of this cosmic drama was something entirely foreign, a traveler from the void between stars known as 3IATLAS. With a plasma cloud nearly half the size of the Sun and growing larger every day, this interstellar visitor was unlike anything astronomers had ever seen. Coincidence? Maybe. But when the heavens flare, the ground quakes, and a visitor from another system drifts closer than ever before, even science starts to wonder whether these events are truly random or whether something far deeper connects them all. For most of human history, the Sun has been a symbol of constancy. It rises, it sets, and life moves to its rhythm. Yet beneath that familiar glow lies a restless engine, one that never truly sleeps. In 2025, that engine stirred awake with a vengeance. Astronomers had been expecting it. The peak of solar cycle 25 was approaching, but no one anticipated just how quickly our star would remind us of its power. The first signs were subtle: faint X-ray flares flickering across NASA's solar observatories, magnetic filaments twisting like serpents across the photosphere, and sudden bursts of plasma ejected into space at hundreds of kilometers per second. Within weeks, the quiet sun of the past decade had transformed into a roaring, boiling sphere of magnetic chaos. Sunspot numbers surged to their highest levels in over a decade, signaling that the star was ramping up to one of its most active phases in modern memory. Then came the storm. On September 14, 2025, a high-speed stream of solar wind, propelled from a vast coronal hole, an open wound in the Sun's magnetic surface, began its 3-day journey toward Earth. These holes, invisible to the naked eye but glaringly bright in ultraviolet wavelength, are gateways where charged particles escape freely into the solar system. When they align with Earth, they can bombard our planet's magnetic field with torrents of plasma. This particular stream was fierce, traveling at speeds exceeding 650 kilometers per second. By the time it reached us, it collided with Earth's magnetosphere like an invisible tidal wave. For most people, the first sign came not from a scientific alert, but from the sky itself. Curtains of light began unfurling far beyond their usual Arctic domain, emerald and violet rivers rippling above Montana, Colorado, even as far south as northern Texas. Social media flooded with videos of people standing in disbelief under glowing skies. Some called it beautiful, others unsettling. But scientists monitoring the KP index, a measure of geomagnetic disturbance, knew exactly what it meant. The storm had reached G3 status, strong by official classification. What made this event especially curious was what it wasn't. It hadn't come from a solar flare or a massive coronal mass ejection, the dramatic explosions most often blamed for space weather chaos. Instead, it was the result of something quieter yet more persistent, a steady stream of plasma from the coronal hole, one that had been rotating across the Sun's equator for weeks. This slow-burn storm built up pressure over time, like a constant wind eroding the defenses of Earth's magnetic shield. Inside that shield, a subtle battle was being fought. As the solar wind slammed into the magnetosphere, it compressed it on the day side and stretched it into a vast tail on the night side. setting off waves of magnetic reconnection, bursts of energy that send charged particles spiraling toward the poles. Those particles collided with oxygen and nitrogen in the upper atmosphere, producing the auroras that painted the sky. But below the light show, invisible effects rippled through the planet. Electric currents surged through power lines and pipelines. Satellite communications flickered. Airline pilots reported navigation anomalies. Deep underground, electrical systems in mines and geological monitoring stations picked up strange readings, faint oscillations that seemed to echo the sun's rhythm. Engineers and geophysicists alike were reminded that even in the 21st century, our supposedly advanced world remains deeply connected to the moods of the star that sustains it. But the storm's most intriguing aspect wasn't its beauty or its technical disruptions, it was its timing, because 3 days later, on September 18th, the Earth trembled. When the Kamchatka Peninsula was rocked by a magnitude 7.8 earthquake, scientists initially dismissed any possible connection to the solar storm as pure coincidence. Earthquakes, they said, are driven by tectonic forces, not space weather, and in the strict geological sense, they're right. The grinding of Earth's plates and the build-up of stress along fault lines are the ultimate culprits behind seismic disasters. Yet, even among researchers, the question lingered: could solar storms play a subtle secondary role, perhaps not creating earthquakes, but triggering them when the conditions were already ripe? It wasn't a new idea. For decades, a fringe subset of geophysicists had been studying potential correlations between solar activity and seismic events. The mainstream scientific community regarded these efforts skeptically, pointing out that statistical overlaps often emerged purely by chance. But this time, the coincidence was uncanny. The solar storm that struck Earth wasn't a brief impulsive flare, it was a prolonged, low-density, high-speed stream that lasted nearly 2 days, precisely the type some theorists had speculated could influence Earth's electrical environment. To understand the argument, you have to think of Earth as more than rock and water. Beneath the crust lies a world of molten metal and flowing charge, a planetary dynamo that generates our magnetic field. Above that, the ionosphere hums with electrical currents induced by solar radiation. During a geomagnetic storm, those currents intensify and shift. They can even seep downward into the crust as telluric currents, following paths of least resistance, often along fault zones saturated with mineralized water. If those fault zones are already under immense stress, some researchers argue, even a minor electromagnetic nudge could act as a trigger, like tapping the final block in a trembling tower. Skeptics counter that the energy involved is far too small. After all, the mechanical forces driving an earthquake are astronomical compared to the faint electrical fluctuations produced by geomagnetic activity. Yet, the Earth isn't always a simple machine of cause and effect. Sometimes it's the smallest disturbances that push an already unstable system past its breaking point. What made September 2025 remarkable wasn't just that the sun flared or that the Earth quaked. It was that these two rare, high-magnitude events occurred in perfect sequence, separated by only 72 hours. To the human mind, that's close enough to raise eyebrows. To the scientific mind, it's close enough to warrant investigation. As data poured in from satellites, observatories, and ground-based instruments, researchers began to notice patterns that went beyond coincidence. The coronal hole responsible for the September storm, designated CH1316, had been visible for weeks, rotating in and out of view as the sun spun on its axis. Each time it faced Earth, geomagnetic activity spiked, and each time, subtle increases in global seismic noise were recorded in the days following. The signals weren't strong enough to prove a direct link, but they were enough to keep scientists watching. Meanwhile, the public narrative took a more dramatic turn. Online discussions exploded with theories, some rational, some less so. Was the Earth reacting to cosmic forces? Was something or someone altering the balance between the sun and our planet? It was the kind of speculation that usually lives on the fringes, but the imagery was too compelling to ignore. The sun awakening after an 11-year lull, the Earth shaking days later, a massive interstellar object drifting into the inner solar system at the same moment. It was a narrative almost too cinematic to be real. But sometimes reality doesn't need fiction's help. As the solar storm faded, scientists observed something unusual. The solar wind density dropped dramatically, even as its speed remained high, a combination known as a solar wind vacuum. In this state, the space around Earth becomes paradoxically emptier, creating fluctuations in pressure across the magnetosphere. Some physicists have proposed that these sudden changes could slightly alter atmospheric and even crustal stresses, though the mechanism remains theoretical at best. Still, in the context of what followed, that strange vacuum felt more like a prelude than a coincidence. It's easy to dismiss such connections when viewed in isolation, but in September 2025, the timing was too perfect, the events too monumental, and the world too interconnected to simply wave away as random. The sun was roaring, the earth was groaning, and somewhere out there a glowing traveler from beyond the stars was drifting into position. For those who pay attention to the hidden rhythms of our planet, these weren't just scattered phenomena, they were signals. The awakening of the sun wasn't just about solar cycles or electromagnetic fields. It was a reminder that the same energy that lights the heavens also stirs the depths of the earth, and as the world would soon discover, when the cosmos begins to move in harmony, the results can shake the very foundation of what we think we know about cause-effect and the fragile balance that holds our world together. Because what happened in September wasn't an ending, it was an overture. The first movement in a chain of events that would challenge everything we thought we understood about the relationship between our planet and the star that gives it life. The sun was awake again, and it wasn't finished speaking. At the edge of Russia's Far East, where snow-capped volcanoes rise from black sand coastlines and steam pours endlessly from the ground, the Kamchatka Peninsula is no stranger to violent change. It is a place born of fire and water, where the Pacific Plate grinds mercilessly beneath the Okhotsk microplate, pushing mountains toward the sky and shoving the seafloor deep into the Earth's mantle. To the untrained eye, Kamchatka's beauty looks eternal. To those who study it, the land is a loaded gun, a region perpetually one tremor away from rewriting its own geography. On July 29, 2025, that gun fired. Without warning, a magnitude 8.8 megathrust earthquake ruptured more than 500 kilometers of fault line beneath the icy Pacific. It was one of the largest quakes recorded in modern history, powerful enough to alter the rotation of the planet by microseconds and displace entire sections of the seafloor. Satellites orbiting hundreds of kilometers above could see the rip. In less than 3 minutes, the tectonic stress built up over decades was released in a single devastating lurch. For hours afterward, the Pacific Ocean itself became a messenger. Tsunami warning systems screamed from Hawaii to Chile, and deep-sea buoys registered pressure changes that sent chills through the scientific community. The waves radiated outward like rings from a stone cast into water, racing across the ocean at nearly 800 kilometers per hour. They struck coastlines in Japan, Alaska, and the western United States, mercifully diminished, but powerful enough to remind everyone of nature's scale. The disaster left a scar that reached far beyond Russia. Yet, as massive as the July quake was, it didn't bring closure. It set the stage for something stranger. Over the following weeks, Kamchatka refused to settle down. The ground kept shifting, like a restless creature that couldn't return to sleep. Seismographs recorded a barrage of aftershocks, more than 40 exceeding magnitude 6.0, several of them strong enough to cause panic. In cities like Petropavlovsk-Kamchatsky, local residents described it as living atop a breathing giant, one that exhaled energy every few days, shaking walls and rattling nerves. When the September 18th quake struck, a magnitude 7.8 monster, many assumed it was just another aftershock. But the deeper researchers looked, the less routine it seemed. This was no minor echo. The September event ruptured a fresh segment of the fault system, one that had remained quiet, even during the July main shock. Its timing, its force, and its alignment with recent solar activity raised uncomfortable questions among scientists and conspiracists alike. In seismology, timing matters. Aftershocks typically follow a predictable decay curve, large at first, then smaller and less frequent as the crust adjusts to its new configuration. The Kamchatka sequence didn't play by those rules. Instead of fading, the seismic energy seemed to pulse in waves, surging back weeks later. To some, it looked as if something external were pumping energy into the system, reawakening stress that should have already dissipated. Of course, traditional science offered explanations grounded in tectonics. When one massive fault ruptures, it redistributes stress throughout the surrounding crust, increasing the likelihood of new quakes nearby. This Coulomb stress transfer can destabilize neighboring fault segments, essentially priming them to slip. That, researchers argued, was exactly what had happened in Kamchatka. The 8.8 event had simply reloaded another part of the same geological gun. But that explanation left one detail unresolved: the uncanny alignment of the September quake with the solar storm that had struck just 3 days earlier. Even in scientific circles, whispers began to circulate. Could fluctuations in Earth's magnetic field influence fault mechanics? Could the same charged particles that painted the skies with aurora also subtly disturb the balance of stresses deep underground? The United States Geological Survey dismissed the idea as speculative. Their official stance was that no proven causal link existed between solar activity and seismic events. Yet privately, some researchers admitted that the timing was interesting. The data, they said, deserved a closer look, because the storm that preceded the earthquake wasn't an ordinary one. The coronal hole responsible, designated CH1316, had been remarkably persistent, blasting high-speed solar wind toward Earth for days on end. The plasma density dropped to record lows even as velocity peaked, creating that peculiar solar wind vacuum. During that period, magnetic field lines across the magnetosphere flexed and reconnected, generating powerful induced currents, and those currents, following the paths of least resistance, didn't always stay confined to the upper atmosphere. Some of them flowed through the crust itself. In regions like Kamchatka, where volcanic minerals and underground water make the rocks unusually conductive, these telluric currents can reach surprising intensities. Geophysical models suggest they can alter pore pressure along fault lines, essentially changing how tightly rocks are locked together. Imagine a rusted hinge suddenly lubricated by invisible forces. It doesn't take much to make it move. Still, even if this mechanism were real, the September quake would require everything to line up perfectly. A heavily stressed fault, a strong geomagnetic disturbance, and a conductive crust ready to transmit electrical energy. In other words, the kind of perfect storm that occurs once in decades, if at all. Yet here it was. The coincidence might have remained an obscure footnote in scientific literature, if not for what came next. In the days following the quake, seismic instruments around the Pacific recorded subtle fluctuations in background tremor rates, not enough to alarm the public, but enough to catch the eye of specialists. It was as though the planet's deep frequencies had shifted slightly, resonating with a new rhythm. These weren't classic aftershocks. They were smaller, more uniform, scattered across vast distances. Some researchers compared the pattern to a bell being struck and continuing to ring long after the impact. And hovering above this restless planet, the interstellar comet 3IATLAS continued its approach. For astronomers, it was a marvel. For those inclined to connect cosmic dots, it was a catalyst. The comet's massive plasma envelope was now interacting with the solar wind in unprecedented ways, distorting magnetic field lines across millions of kilometers. To a few outside-the-box thinkers, that meant one thing: the heliosphere. The bubble of charged particles surrounding the sun wasn't behaving normally. If the magnetic environment of the solar system was in flux, then Earth, as part of that system, might be feeling those effects directly. Suddenly, the idea that solar activity could trigger earthquakes didn't sound quite as implausible. It sounded like part of a much larger puzzle. Mainstream scientists, of course, urged caution. Correlation does not imply causation, they repeated. But they, too, couldn't ignore the mounting anomalies. The geomagnetic storm's peak coincided almost perfectly with subtle ionospheric disturbances detected over the Pacific Rim. Radio wave measurements showed unusual interference patterns. Even atmospheric pressure maps displayed faint ripples, inconsistent with standard models. Something was happening in Earth's energy systems, something synchronized with events beyond the atmosphere. When the September quake struck, local residents described a strange silence before the shaking began, a stillness that felt heavy, as though the air itself were holding its breath. Fishermen off the Kamchatka coast reported seeing eerie glows under the water, like dim lightning flickering through the depths. These anecdotes were easy to dismiss as nerves and imagination, but combined with instrument readings, they painted a picture that was difficult to ignore. By the time daylight returned, the world was once again reminded of Kamchatka's volatile nature. Roads cracked, buildings listed, and tsunami sirens wailed into the cold morning air. The quake triggered underwater landslides, stirring the sea into short-lived surges that battered nearby coastlines. Thankfully, the region's low population density meant casualties were minimal, but for geologists, the event left behind more questions than answers. Because in that brief span of 72 hours, three forces, solar, terrestrial, and interstellar, had converged in a pattern that defied easy explanation. The official reports filed by seismic agencies called it an expected aftershock sequence. But for a growing number of researchers tracking solar data, magnetic flux variations, and plasma dynamics, the term expected felt like denial. They saw patterns repeating in the noise periodicities that matched the solar wind's pulse, correlations between geomagnetic indices and seismic strain rates that couldn't easily be dismissed. Kamchatka, it seemed, was not just reacting to tectonic pressures. It might have been responding to the rhythms of the sun itself. And if that was true, if even a fraction of the Earth's seismic activity could be influenced by fluctuations in space weather, then humanity's understanding of how this planet works would need rewriting from the ground up. What made the Kamchatka event so unsettling wasn't just their scale, but their implication. They hinted that the Earth's crust, far from being isolated from cosmic forces, might be part of a delicate electromagnetic network spanning the solar system. In that network, the sun's eruptions, planetary alignments, and even passing interstellar objects could act like tuning forks, sending ripples through a system vast enough to include everything from auroras to earthquakes. For centuries, humans have separated the heavens from the Earth, astronomy from geology, space from soil. But in the wake of Kamchatka's twin quakes and the sun's awakening, that distinction was starting to blur. The data suggested that our planet, like a drum, might resonate to cosmic rhythms more profoundly than we've ever realized. And as the world moved closer to October 2025, when solar activity, planetary alignments, and the arrival of 3IATLAS would all peak simultaneously, one question began echoing across scientific communities and conspiracy forums alike. Was Kamchatka a warning, or merely the first note in a much larger cosmic symphony, still building toward its climax? There's a theory that our planet hums with a frequency, a faint inaudible resonance born from the constant motion of its atmosphere, oceans, and molten heart. Most of the time this vibration is steady and harmless, like the rhythm of a sleeping creature, but every so often something disturbs the balance, and the hum grows louder. Some scientists call it background noise. Others believe it's the sound of the Earth responding to forces far greater than we understand. To grasp the idea of an earthquake generator, we need to leave behind what we think we know about where seismic energy comes from. The traditional model is straightforward. Tectonic plates move, stress accumulates, and when the rocks can't take it anymore, they slip, releasing energy as an earthquake. It's mechanical, predictable, and beautifully simple. But what if that's only half the story? What if the Earth's surface, those fault lines we watch so carefully, isn't just a product of internal motion, but a receiver for signals from beyond? That's where the solar wind vacuum theory enters the picture. Imagine the space around Earth as an ocean of invisible particles, constantly streaming from the sun. These charged particles, mostly electrons and protons, flow outward at incredible speeds, forming what we call the solar wind. When this stream interacts with Earth's magnetic field, it shapes and distorts the magnetosphere, creating magnetic storms, auroras, and sometimes chaos in our communication systems. But under rare conditions, something even stranger happens. Occasionally, during the passage of a coronal hole or a prolonged geomagnetic storm, the solar wind becomes thin, its density drops dramatically while its speed increases. It's as though space itself becomes less dense, a cosmic low-pressure zone sweeping across the planet's magnetic shield. Some researchers refer to this as a solar wind vacuum. To most astrophysicists, it's simply an oddity of plasma physics. But to a few independent researchers studying seismic patterns, this vacuum might hold the key to one of Earth's oldest mysteries. The logic goes like this. When the solar wind pressure drops sharply, Earth's magnetosphere expands. That expansion causes shifts in the distribution of electrical currents flowing between the ionosphere and the ground, currents known as telluric currents. These invisible rivers of energy flow through the planet's crust, guided by conductive materials like metal ores, groundwater, and fault lines. During normal conditions, they're weak and harmless, but when geomagnetic activity spikes or the solar wind fluctuates wildly, these currents intensify, sometimes reaching hundreds of amperes. Now, picture what happens when those currents travel through rocks already under immense tectonic stress. The energy doesn't break the rocks directly, it changes the microscopic conditions inside them. It can heat pore fluids, alter chemical bonds, or slightly shift the balance between locked and slipping segments of a fault. In other words, if a fault is already at its breaking point, a small electromagnetic nudge could in theory push it over the edge. That's the essence of the earthquake generator hypothesis. But under the right cosmic conditions, electromagnetic fluctuations born from solar storms, solar wind vacuum, or even interactions with distant objects can act as the final trigger for earthquakes that are already primed to happen. It's a radical idea, and the scientific establishment has resisted it for decades. The United States Geological Survey maintains that no statistically significant correlation exists between geomagnetic disturbances and seismic events. Yet, when you look at the data from September 2025, it's hard not to wonder. During the G3 geomagnetic storm, ground-based magnetometers detected persistent magnetic oscillations lasting over 48. At the same time, ionospheric monitoring stations around the Pacific recorded unusual disturbances, ripples in electron density that seemed to pulse in harmony with the solar wind's rhythm. Then 3 days after the storm began, Kamchatka erupted with seismic fury. Coincidence? Maybe. But it's exactly the kind of sequence that the earthquake generator theory predicts. To understand how it might work, we have to think electrically. Earth isn't just a rock orbiting the sun, it's a conductor. Its molten core, metallic mantle, and salty oceans all interact with electromagnetic fields in complex ways. When the solar wind changes, Earth's electric environment changes with it. If the crust behaves like a vast circuit board, then solar storms are the surges that occasionally overload its components. In 2025, the coronal hole labeled CH1T116 became the focal point of this debate. It had been facing Earth multiple times as the sun rotated, sending wave after wave of high-speed solar wind in our direction. Scientists noticed that each time CH1T16 came into alignment, geomagnetic activity spiked, and in several cases global seismic energy release increased within a few days. The effect wasn't uniform, but the correlation was there. Skeptics argued that with thousands of earthquakes occurring around the world every year, some overlap with solar storms is inevitable. But proponents countered that the timing and magnitude patterns were too consistent to ignore. They pointed to clusters of strong quakes following extended solar wind vacuums, arguing that these weren't random alignments but hints of a deeper relationship. Some even went further, suggesting that the interaction wasn't limited to our planet. They proposed that the entire solar system behaves like a gigantic electrical circuit, with each planet, moon and comet participating in a vast network of charged particles and magnetic fields. In that framework, the sun isn't just a source of light and heat, it's the central power supply, and if something, say an interstellar visitor like 3IATLAS enters that system, it could alter the electrical balance, creating conditions that ripple through the entire network. To traditional astrophysicists, this sounds like science fiction, but the evidence of 3IATLAS's influence was growing. Its plasma coma was already massive, hundreds of thousands of kilometers wide, and it interacted with the solar wind in measurable ways. Some models suggested that its presence could slightly distort the heliospheric magnetic field, redirecting streams of charged particles and creating interference patterns that extended toward Earth's orbit. If that was true, it might mean that our planet was caught in a kind of electromagnetic crossfire, an invisible tug-of-war between the sun's energy and the comet's vast ionized envelope. And when that kind of pressure builds, even the smallest fluctuation can have consequences. To visualize this, imagine a glass of water filled to the brim. You can stare at it for hours without a drop spilling, but the slightest vibration, a footstep, a breath can send the surface tension breaking. The earthquake generator theory suggests that Earth's crust works the same way. The stress is already there, balanced on the edge of release. All it takes is a faint electromagnetic tremor, perhaps from a geomagnetic storm, perhaps from a solar wind vacuum, to tip it over. Of course, not everyone buys it. Many seismologists insist that the energy scales involved simply don't match. The mechanical forces behind an earthquake dwarf any known electromagnetic input from space, but proponents of the theory counter that the size of the trigger doesn't have to match the scale of the event. It only has to arrive at the right moment in the right place. After all, a single grain of sand can start an avalanche if it lands on a slope already at its critical angle. In September 2025, that critical slope may have been Kamchatka. The quake's timing wasn't the only anomaly. In the hours leading up to it, instruments across the Pacific recorded subtle electromagnetic fluctuations, almost like a heartbeat quickening before a shock. The signals were faint but synchronous, spreading across vast distances faster than seismic waves could travel. To those who studied them, It looked as though something had momentarily synchronized the planet's electromagnetic and mechanical systems, a resonance between Earth's crust and its surrounding plasma environment. What could cause such synchronization? No one knew for sure. Some blamed the coronal hole's persistent high-speed stream. Others pointed to interactions between the solar wind and the expanding coma of 3IATLAS. But whatever the mechanism, the result was undeniable. A planet under stress had responded to a cosmic pulse. The earthquake generator remains a controversial concept, but its implications are staggering. If even part of it is true, it means our planet's seismic activity isn't entirely self-contained. It's part of a larger cosmic rhythm, a conversation between Earth and the Sun, mediated by the invisible currents of space. It would also mean that predicting earthquakes might one day involve watching the stars as much as the ground. For now, the theory remains on the fringe, its proponents dismissed by mainstream academia. But as solar activity intensifies and more interstellar objects drift through our cosmic neighborhood, the patterns are becoming harder to ignore. The data from 2025 didn't provide proof, but it offered something tantalizing, a pattern too precise to be random, yet too complex to fully explain. And if the Sun, through its storms and vacuums, truly holds the power to whisper into Earth's crust, then the term earthquake generator might not be metaphorical after all. It could be literal, a vast celestial machine operating across billions of kilometers, capable of turning cosmic energy into planetary motion. In that sense, the September storm and the Kamchatka quake weren't separate events. They were consecutive beats in a single planetary rhythm, one driven not by tectonics alone, but by the pulsing heart of the Sun itself. And as that heart continues to quicken, the question becomes not whether Earth will respond, but how much louder the next note in this cosmic symphony will be. Sometimes timing alone feels like a message. On September 13, 2025, a quiet astronomical alignment took place, one that few outside the scientific community even noticed. Mercury, the smallest planet in our solar system and the one closest to the Sun, reached what astronomers call superior conjunction, the moment when it sits directly behind the Sun from Earth's perspective, forming a perfect straight line across space. In that instant, the Sun, Mercury, and Earth were connected by an invisible thread stretching nearly 50 million kilometers. To most, it was just another celestial footnote. But less than 24 hours later, Earth was hit by one of the most intense geomagnetic storms of the decade. For scientists, the timing was coincidence. For everyone else watching the skies, it was too precise to ignore. The G3 storm of September 14th wasn't born from one of the Sun's dramatic outbursts. There was no towering solar flare or explosive coronal mass ejection to blame. Instead, it came from something far subtler, an enormous coronal hole named CH1316 that had rotated into position days earlier. Through that gap in the Sun's magnetic field, high-speed solar winds streamed outward like a jet of invisible fire. As it raced across space, it carried with it charged particles traveling faster than 650 kilometers per second, enough to circle Earth in under a minute. When that stream struck Earth's magnetosphere, the collision was invisible yet cataclysmic. The magnetic field surrounding our planet buckled, compressed, and twisted, generating electrical currents that raced through the upper atmosphere and into the crust below. For 2 days, the planet was engulfed in an electromagnetic storm that reshaped the behavior of everything from satellites to migratory birds. The KP index, a measure of geomagnetic disturbance, spiked to levels not seen in years. The skies responded in kind. Curtains of neon light shimmered as far south as Kansas, Missouri, and northern Spain. To the average observer, it was breathtaking. To researchers, it was perplexing. Forecasts had predicted only a moderate storm, a G2 at most. Yet, without warning, the event intensified. Magnetometers around the world registered sudden surges in current strength, far exceeding expectations. Power grid operators scrambled to mitigate induced currents that threatened to overload transformers. Radio communications faltered. GPS accuracy degraded. It was as though the Earth's invisible shield had been struck with a force greater than anyone had anticipated. That's when the whispers began. For centuries, humans have attributed cosmic meaning to planetary alignments. Astrologers have built entire systems of belief around them, while scientists have long dismissed such ideas as superstition. And yet, even within the realm of physics, the question lingered. Could planetary configurations subtly influence the solar wind or the magnetic environment of the heliosphere? Not through gravity, that effect would be negligible, but through electromagnetic coupling. To understand how this might work, imagine the solar system not as a static clockwork of planets orbiting the Sun, but as a vast electrical network. The Sun is the power source, continuously emitting streams of charged particles that flow outward like currents in a wire. Each planet, with its magnetic field and ionosphere, acts as a circuit component, a resistor, a capacitor, an inductor shaping and redirecting those currents in complex ways. When planets align, their combined magnetic and plasma interactions could, at least in theory, alter the structure of the heliospheric current sheet, the immense spiral of electrical current that winds through the solar system. Normally, such shifts would be too faint to notice. But on September 13th, as Mercury aligned behind the Sun, the solar wind's behavior changed dramatically. Data from NASA's ACE spacecraft recorded fluctuations in particle velocity and density that didn't match any known solar pattern. Within hours, Earth's magnetosphere was struck by the intensified stream that would trigger the G3 storm. Coincidence? Most likely, said the experts. Still, the pattern was curious enough to fuel speculation. The alignment, the storm and the sudden overperformance of CH1316 solar wind stream all happened in the same narrow window of time. The odds of that were slim. Some researchers began to ask whether planetary alignments could modulate the flow of plasma in the heliosphere, not by pulling on it gravitationally, but by changing its electromagnetic impedance the way a network of resistors alters a circuit's current. The analogy was simple. If the Sun's plasma output is a current, and the planets act as conductive nodes, then certain alignments might momentarily shift the balance, amplifying or redirecting the flow. When that amplified flow reached Earth, the result would be storms stronger than predicted, like the one we had just witnessed. For now, the theory was unproven, but the data from that week refused to settle quietly. The G3 storm had exceeded predictions by nearly 40%. Its arrival was perfectly timed with Mercury's alignment, and it triggered a cascade of atmospheric and terrestrial effects that rippled for days. At high altitudes, airliners diverted routes as communication blackouts struck over the polar regions. In Alaska, auroras appeared at midday, faint but visible against the pale sky. Amateur radio operators across the globe recorded bursts of interference unlike any seen in previous storms. Even whales in the North Pacific exhibited unusual migration patterns, veering hundreds of kilometers off their normal routes. But below all of that, deep beneath the ocean and crust, something else was happening. The storm's electromagnetic energy didn't stop at the atmosphere. It induced electrical currents in the ground itself, known as geomagnetically induced currents, GICs. Power companies have long feared these invisible surges because they can wreak havoc on infrastructure, frying transformers and corroding pipelines. But in regions rich in conductive minerals like Kamchatka and Alaska, GICs do more than damage equipment. They seep into the Earth's crust, and this is where the story turns strange. Measurements from a network of seismoelectric sensors around the Pacific Rim detected faint electrical pulses traveling through the crust in the hours following the storm's peak. These weren't seismic waves. No earthquakes had occurred yet. They were electromagnetic anomalies, oscillating at frequencies too low for typical lightning activity, too steady to be random noise. The signals matched the timing of the geomagnetic fluctuations overhead. 3 days later, Kamchatka's fault zone ruptured in a magnitude 7.8 earthquake. It's tempting to connect the dots to imagine that the alignment of Mercury, the surge of solar wind and the ensuing storm had somehow conspired to nudge an already stressed fault into failure. The notion sounds fantastical, almost mythic, planets aligning to stir the Earth's core, but the physical mechanisms, while speculative, aren't entirely beyond comprehension. Electrical currents flowing through a fault can alter the pressure of fluids trapped within the rock. Those fluids act like lubricants, reducing friction along the fault plane. A sudden shift in current strength could, in principle, change that balance just enough to trigger a slip. It's the same principle used in laboratory rock mechanics, where applying an electrical field can make brittle materials fracture at lower stress levels. If the Kamchatka fault was already loaded close to its breaking point, and after July's 8.8 quake it almost certainly was, then even a tiny electromagnetic disturbance could have been the proverbial straw. The alignment of Mercury might seem irrelevant, but in the broader cosmic circuit, timing matters. The superior conjunction meant that Mercury's magnetosphere was directly behind the Sun, possibly influencing how the solar wind's magnetic field lines reconnected and streamed toward Earth. If those reconnections altered the flow of the coronal hole's plasma even slightly, it could explain why the storm was stronger than expected, and why the geomagnetic currents that reached Earth were so unusually intense. It's easy to dismiss such connections as coincidence. But as with so many mysteries in science, the line between coincidence and causation often blurs when patterns repeat. In the following weeks, smaller but similar storms aligned eerily with minor planetary configurations, Venus oppositions, Earth-Mars syzygies, and each time seismographs registered subtle upticks in activity. The data hinted at a rhythm, a synchronization between celestial geometry and terrestrial restlessness. If this pattern is real, it suggests that our solar system operates as an interconnected electrical organism, one in which planetary alignments subtly modulate the flow of energy from the Sun, with downstream effects on every magnetic body within its reach, including Earth. Most scientists remain cautious. After all, extraordinary claims require extraordinary proof. But even within NASA and ESA's heliophysics divisions, quiet discussions began circulating after September 2025. The storm that shouldn't have been so strong was now being re-examined under new hypotheses. Could Mercury's alignment have shifted the structure of the heliospheric current sheet, focusing more energy toward Earth? Could the simultaneous presence of interstellar comet 3IATLAS, its massive plasma cloud interacting with the solar wind, have amplified those effects further? There was no consensus, only an uncomfortable realization. Too many rare events were happening too close together. And as scientists raced to analyze the data, the clock kept ticking toward October, a month that would bring even more alignments, more solar activity, and the closest approach of 3IATLAS. If September was the spark, October would be the ignition. The G3 storm had shown us that the universe's timing is not random, that celestial geometry can align with earthly consequence in ways we barely understand. Whether through electromagnetic coupling, solar resonance, or something entirely unknown, the cosmos had demonstrated its power to reach across millions of kilometers and stir the deepest foundations of our world. And as the Sun's activity continued to climb, the question was no longer whether these forces were connected, it was how far the chain of connection might extend. Because if planetary alignments could amplify storms and storms could shake the ground, then perhaps the sky above us and the earth beneath our feet were never as separate as we believed. Long before telescopes could see it, something vast was already drifting toward us through the black. It had been traveling for millions, perhaps billions of years, a fragment of another star system flung into the interstellar void by ancient violence. For most of its journey it moved unnoticed, a silent spark crossing the emptiness between suns. Then in mid-2025, it entered the outer reaches of our solar system and caught the eye of a sky survey scanning for new comets. The discovery was labeled 3IATLAS, marking it as only the third confirmed interstellar object ever detected by humans. At first, astronomers thought it was routine, a comet-like body, perhaps a few kilometers across, following a hyperbolic trajectory that would send it swinging past the Sun before vanishing forever into the darkness. But 3IATLAS wasn't routine. It wasn't like anything they'd seen before. When the first high-resolution images came in, scientists realized its coma, the glowing halo of gas and dust surrounding the core, was unimaginably huge. Even at its early approach, the cloud of ionized material stretched millions of kilometers, dwarfing entire planets. By late August, it had expanded to nearly half the diameter of the Sun itself. If you could have stood on Mercury's orbit and looked outward, 3IATLAS would have filled a chunk of the sky like a pale, ghostly sphere. The object's behavior defied logic. Normal comets brighten gradually as they near the Sun, their icy surfaces sublimating into vapor. But 3IATLAS flared suddenly, then dimmed, then flared again, as though pulsing with an unseen rhythm. Some attributed it to jets of gas bursting from its surface. Others wondered if its rotation or internal composition was somehow amplifying solar interactions in ways no one yet understood. Whatever the cause, one thing was clear. 3IATLAS was not just a passive traveler. It was reacting to sunlight, to magnetic fields, and perhaps even to the solar wind itself. What fascinated scientists most wasn't just its size or brightness, but its electromagnetic footprint. Instruments across the world detected subtle but consistent anomalies in the solar wind's flow as the object moved closer. The charged particles streaming outward from the sun seemed to curve and accelerate in unusual ways near its path, as though being drawn into an unseen magnetic well. Space physicists began calling it the Atlas effect, a temporary distortion in the heliospheric current sheet, the vast wavy structure of magnetic energy that extends throughout the solar system. To understand how strange this was, consider that the sun's magnetic field governs everything within its domain. It's the architect of space weather, the invisible force shaping planetary orbits, radiation belts, and solar storms. Normally it follows predictable patterns, unless something powerful disturbs it. For an object only a few kilometers wide to influence that system at all should have been impossible. Yet data from NASA's Parker Solar Probe and the European Solar Orbiter both hinted that something was off. The plasma density near the comet's trajectory dropped sharply, while magnetic field lines twisted in configurations that didn't match expected models. In other words, 3IATLAS wasn't just moving through the solar wind, it was altering it. As word spread through the scientific community, so did the unease. A handful of researchers privately speculated that the comet might not be entirely natural, not in the sense of alien technology, but as an exotic remnant of a long-dead star system, forged in magnetic fields far stronger than our sun. If it carried remnant magnetism, even a weak one, it could interact with solar plasma in extraordinary ways. A magnetic body that large moving through the solar wind could act like a conductor, absorbing, redirecting, or even amplifying electromagnetic currents. That idea was electrifying and unsettling, because if 3IATLAS was reshaping the flow of charged particles in the inner solar system, it meant Earth was downstream of something unprecedented. By early September, as the sun erupted with activity and the Kamchatka region trembled, 3IATLAS was approaching perihelion, the closest point in its orbit to the sun. Observatories across the world focused on it, watching as the coma brightened with a pale cyan glow. Spectroscopic data revealed traces of exotic molecules, carbon chains, cyanide radicals, and something even rarer, ionized iron compounds, typically found only in extreme magnetic environments. That discovery deepened the mystery. What kind of journey had this object survived to arrive here, and what could it carry within? For planetary scientists, 3IATLAS became a living experiment. They tracked how its enormous plasma envelope interacted with the solar wind. They watched as the magnetic field around the comet pulsed in sync with fluctuations detected near Earth. Timing that again felt too precise to ignore. When the G3 geomagnetic storm hit on September 14th, instruments recorded an anomaly in 3IATLAS's tail, a sudden expansion followed by rapid collapse, as if it had inhaled and exhaled electromagnetic energy. It was almost poetic, the interstellar traveler breathing with the sun. But for others, the synchronicity was unsettling. Online discussions exploded with theories ranging from plausible to paranoid. Some claimed 3IATLAS was a fragment of a Dyson structure, a technological relic built to harness starlight. Others suggested it was a magnetic sponge, absorbing and redirecting solar energy in ways we couldn't yet comprehend. A few fringe theorists even proposed that its arrival had triggered the sun's reawakening, acting as a catalyst for the surge in solar activity. Mainstream scientists dismissed those ideas, but privately, even some of them were intrigued. The coincidence of timing was impossible to ignore. The sun had entered one of its most active phases in over a decade, just as this colossal, magnetically strange object entered the inner solar system. Whether connected or not, it was the kind of overlap that stirred the imagination. And if the comet's influence extended beyond solar plasma, if it truly altered electromagnetic conditions within the heliosphere, then Earth would inevitably feel the ripple effects. One particularly daring paper from a European research group proposed that 3IATLAS might act as a temporary interstellar node, a point of interaction between the magnetic field of our sun and the residual magnetic fields of interstellar space. If that were true, the object could momentarily connect two vast electromagnetic domains, allowing energy to flow in ways never before observed. That might explain the anomalies in solar wind pressure, the erratic behavior of the magnetosphere, and even the timing of the Kamchatka quakes. In essence, 3IATLAS could have become a bridge between our star and the galaxy beyond, a cosmic switch flicked on by chance alignment. For ordinary people, such ideas sounded apocalyptic, But for those who study space weather, the prospect was exhilarating and terrifying in equal measure. It suggested that interstellar visitors could do more than just pass through. They could temporarily rewrite the electromagnetic landscape of an entire solar system. By late September, as 3I/ATLAS neared its closest approach, its behavior grew even more erratic. Astronomers watched as jets of material erupted from its surface, releasing bursts of ionized gas that spiraled like luminous storms. The comet's tail, already tens of millions of kilometers long, bent sharply as if following an invisible current. Ground-based magnetometers on Earth detected subtle disturbances that matched those movements almost instantaneously, a hint that electromagnetic coupling between the comet and the solar wind might be occurring faster than light-speed particles could account for. Of course, physics forbids faster-than-light interaction, so scientists dismissed it as data coincidence. But others weren't so sure. In an interconnected plasma medium like the solar wind, changes in magnetic topology can propagate in complex wave-like ways that mimic near-instant communication across enormous distances. To the untrained eye, it looks impossible. To plasma physicists, it's merely poorly understood. Still, the coincidences kept piling up. During 3I/ATLAS's closest approach, solar activity spiked again. Multiple coronal mass ejections erupted from the sun's surface within hours, aimed toward the same region of space the comet occupied. The solar wind intensified, carrying massive bursts of charged particles through the heliosphere. Earth's magnetic field shuddered under the impact, though this time the storm barely reached G2 levels, less severe than before but longer lasting, as if the energy were being sustained rather than released. It was almost as if something out there was feeding the storm. If 3I/ATLAS truly interacted with the solar magnetic field on that scale, it might have amplified the sun's emissions like a resonant chamber. In musical terms, it could have been acting as a subwoofer in the cosmic symphony, magnifying certain frequencies, shaping others, and creating beats that rippled through space. Earth, caught within that resonance, would experience the consequences through geomagnetic storms, atmospheric disturbances, and maybe, if the theories hold any truth, even seismic responses. By the end of September, the comet began to drift outward again, its massive coma slowly dissipating as it receded from the sun's heat. But the effects it left behind were measurable and strange. Satellite readings continued to show irregularities in solar wind velocity. Auroral activity remained unusually high. Even as the comet moved away, the Earth's magnetic field behaved as though something still tugged at it from afar. To most of the world, 3I/ATLAS was just another headline, a curiosity, a beautiful object in the night sky. But to those watching closely, it represented a paradigm shift. It suggested that our solar system was not an isolated bubble, but a porous breathing entity constantly influenced by forces beyond. And perhaps most unsettling of all, it reminded us that space is not empty. It's alive with energy, with currents, with connections we've only begun to glimpse. If 3I/ATLAS was truly the messenger some believe it to be, its message was clear. The universe is not separate systems and stars, but one vast field of energy, bound together across light years. What happens in one corner can echo in another, and when that echo passes through our tiny, trembling world, it leaves more than beauty in the sky. It leaves a question hanging in the charged air. What else is out there waiting to make itself felt? Every planet, every moon, and even the smallest grain of dust orbiting the sun is bound together by something invisible. A vast pulsing field of energy that threads through the solar system like an intricate web. We call it the heliosphere, but that word barely captures its scale. It is not simply a bubble of plasma or a region of space. It is a living, electric ocean in which the Earth swims like a small, luminous fish. And in September 2025, that ocean stirred. For decades, scientists have understood that the sun doesn't merely radiate light, it breathes. Each breath is a pulse of charged particles known as the solar wind, a constant stream of electrons and protons that flows outward in every direction. This wind fills the heliosphere, shaping its magnetic boundaries and connecting every planet, asteroid and comet in a continuous electrical network. Most of the time, it flows gently, unseen and unremarked upon, but when the sun awakens, that calm current becomes a storm-tossed sea. In 2025, the sun's breathing quickened. Solar cycle 25 was approaching its peak, and the sun's magnetic fields were twisting and snapping with renewed vigor. Coronal holes widened, flares erupted, and waves of high-energy plasma rolled across the heliosphere. Yet what made this period extraordinary wasn't the activity itself. It was the complexity of the electromagnetic web that began to reveal itself as these forces interacted. For the first time, humanity could see hints of the invisible threads that bind space together. The first clue came from satellites orbiting Earth. The solar wind, normally steady in direction and speed, began to oscillate in rhythmic waves. The Parker Solar Probe, which was then near the Sun's equator, detected currents that pulsed like a heartbeat, regular, almost biological. The amplitude of these waves increased whenever the solar wind passed through the magnetic wake of 3IATLAS, the interstellar visitor whose massive plasma envelope was now distorting local fields. At the same time, Earth's magnetosphere, the protective bubble formed by its own magnetic field, began responding in strange ways. During geomagnetic storms, it's normal for the magnetosphere to compress and expand, but this time, the oscillations didn't match solar activity alone. They came in layered patterns, as though multiple sources were tugging at the planet's magnetic shell simultaneously. Some physicists described it as cross-field coupling, a situation where magnetic domains from different origins begin to interact directly, exchanging energy in bursts and surges. It was as if the Sun, Earth, and comet had become linked in a shared circuit, three charged bodies exchanging invisible power through the plasma currents of space. To visualize this, imagine the heliosphere as a giant spiderweb made of light. Each planet, each magnetic field is a node where strands converge. When one node moves, vibrations travel along the threads, affecting everything else connected to the web. The Sun's magnetic field provides the structure, but the planets act as resonators, amplifying and reflecting those vibrations back into the system. Normally, these ripples are too subtle to detect, but when a massive event like a geomagnetic storm or an interstellar intruder disturbs the web, the entire structure hums. That hum is what scientists began hearing in September. Magnetometers on satellites, on the ground, and even buried deep underground all recorded synchronized fluctuations. The frequencies varied from region to region, but the pattern was unmistakable. The planet was responding as one system, vibrating in time with the solar wind. The Earth's magnetic poles flickered like the ends of a tuning fork. The ionosphere, the layer of charged particles in the upper atmosphere, shimmered with unusual currents, forming luminous bands that extended far beyond normal auroral zones. At first it seemed beautiful, harmless, a cosmic light show, but beauty in nature often hides power, and in this case the power was immense. The geomagnetic energy flowing into Earth's upper atmosphere induced electric fields across the ground, creating what are known as geomagnetically induced currents, or GICs. Usually these currents are weak, barely measurable, but during the September storms, they surged to levels not seen since the early 2000s. Power grid operators in northern regions reported sudden voltage fluctuations. Long-distance pipelines began registering corrosion rates that spiked inexplicably overnight. Deep-sea communication cables picked up faint oscillations, as though the very ocean was carrying an electrical pulse. Yet the most curious data came from geological monitoring stations. Instruments designed to measure strain in the Earth's crust began detecting microvariations synchronized with geomagnetic shifts. The readings weren't seismic, they didn't indicate actual movement, but they hinted at something else: electromagnetic pressure building and releasing within the planet's lithosphere. For years, this kind of correlation had been dismissed as coincidence or noise, but now, with multiple events happening in tight synchronization, the Sun's eruptions, the arrival of 3IATLAS, the Kamchatka quakes, the idea that Earth's crust could be influenced by solar magnetism no longer seemed absurd. If space is an electrical web, and our planet is part of it, then the forces moving through that web might sometimes be strong enough to make the Earth tremble. The deeper scientists looked, the stranger it became. Data from the European Space Agency's cluster mission, a fleet of satellites studying Earth's magnetosphere, showed that magnetic field lines connecting the Earth and Sun were behaving like elastic bands, stretching and snapping back with explosive force. These magnetic reconnection events released bursts of plasma that spiraled down toward the poles, triggering auroras visible even from Central Europe. But the timing of those reconnections matched peculiar surges and seismic noise along fault zones across the Pacific Rim. Could it be coincidence? Possibly. But some physicists began to suspect a more elegant explanation: resonance. In any interconnected system, energy can build up when oscillations synchronize. It's how a singer can shatter a glass by matching its resonant frequency, or how a bridge can collapse when soldiers march in step. The electromagnetic web of the solar system is no different. If the natural frequencies of Earth's magnetic field align with fluctuations in the solar wind, energy can accumulate rather than dissipate. When that resonance reaches a threshold, the stored energy must go somewhere into the atmosphere, the oceans, or perhaps even the crust. This wasn't just speculation. Measurements taken from magnetotelluric stations, devices that monitor both electric and magnetic fields in the ground, showed surges that lasted for hours during the height of the storm. The direction of these currents corresponded with known fault lines, as if the energy sought paths of least resistance. To some, this was proof of electromagnetic coupling between the Sun and Earth's geology. To others, it was merely an intriguing anomaly. But even skeptics couldn't deny that something unusual was happening. The planet was behaving like part of a much larger electrical machine, and that machine, it seemed, was starting to hum louder. As September gave way to October, the Sun's surface erupted again, this time with a series of flares that rippled through the heliosphere. The energy wasn't directed toward Earth, yet the planet still reacted. Auroras appeared without direct solar impact, indicating that electromagnetic disturbances were propagating through the heliospheric web itself, not simply riding the solar wind. It was as though Earth was feeling the tremors of distant events connected through invisible filaments of plasma. That realization changed everything. It meant that the Sun doesn't act alone in shaping space weather. Instead, every charged object from Mercury to Jupiter, from the tails of comets to the magnetospheres of distant planets, plays a part in a complex network of feedback loops. A storm on one side of the system could subtly influence magnetic conditions on the other. The interstellar comet 3IATLAS had introduced a wild card into that network. Its enormous plasma envelope, rich in ionized gases, acted like a temporary node in the web, a foreign connection splicing into the Sun's circuitry. The disturbances it caused weren't just localized, they rippled outward, bending field lines and altering how energy flowed through the solar system. For the first time, Earth was connected not just to its star, but to something beyond it. Some scientists compared it to a drop of ink falling into clear water. The ink spreads, altering the flow of currents and creating patterns that persist long after the original drop is dispersed. The passage of 3IATLAS, they said, might leave behind similar imprints, subtle changes in the solar wind's structure, electromagnetic echoes that continue to influence planetary weather and magnetism for years. Others saw something deeper. They argued that what we were witnessing wasn't just a temporary disturbance, but a revelation of the solar system's true nature. Space, they said, is not a void, but a medium alive with energy structured by electricity and magnetism. Planets aren't isolated bodies, they're connected nodes in a galactic circuit. When one node changes, the others respond. The events of 2025 were a demonstration of that principle on a grand scale, and perhaps they warned also a reminder. Because if the heliosphere truly operates as an electromagnetic web, then its stability depends on balance. Too much energy in one region, too strong a flare, too dense a plasma wave, and the system could destabilize. The Sun's outbursts might trigger chain reactions reaching far beyond our current understanding. A powerful enough alignment or an interstellar object with the wrong properties could amplify those effects until they cascade through the web like a storm through power line. No one knows what that would look like. Maybe it would be nothing more than a spectacular light show, or maybe it would be something far more profound, a planetary scale event, where the boundaries between Earth, Sun, and space dissolve completely, revealing the hidden circuitry that has always connected them. In 2025, we caught a glimpse of that circuitry. For a few weeks, the electromagnetic web shimmered into visibility, its patterns traced by auroras, quakes, and storms. Then, as quickly as it had awakened, it began to fade. The Sun quieted slightly, the geomagnetic disturbances subsided, and the data streams returned to their familiar rhythms. But the memory remained, a record of a moment when Earth seemed to pulse in time with the cosmos. And for those who understood what they'd seen, one truth became undeniable. The universe is not a collection of separate worlds drifting in silence. It is one vast connected system, a web of energy where every spark, every storm, and every tremor is part of the same unfolding story. The question now wasn't whether the web existed, it was when it would sing again, and how loud the next note would be. In the days following the G3 storm, The sun fell into an eerie calm, the auroras faded, the magnetometers settled, the chatter of cosmic particles striking the upper atmosphere softened to a whisper. To the untrained eye, it seemed as though the storm had passed and the world was returning to balance. But beneath that calm, something stranger and perhaps more dangerous was brewing. Space itself had changed. Solar physicists began noticing an anomaly in the data. The density of the solar wind had plummeted, not gradually but suddenly, like air rushing out of a punctured balloon. The velocity remained high, over 600 kilometers per second, yet the number of particles within that wind dropped to a fraction of what models predicted. For the first time in years, the plasma stream flowing past Earth was thinning faster than the instruments could record. It was as though the solar system had exhaled and forgotten to breathe back in. They called it a solar wind vacuum, a rare and poorly understood phenomenon, where the flow of charged particles from the sun dips dramatically, leaving the space around Earth almost empty. To the casual observer, that sounds harmless. After all, space is already a vacuum. But in the fragile balance of the heliosphere, density matters. Every particle in the solar wind contributes to the invisible pressure that keeps Earth's magnetic field compact and stable. When that pressure drops, the magnetosphere expands outward like a balloon released from a squeeze, and when it expands too far, things start to get weird. During a vacuum event, the protective bubble around Earth doesn't just grow, it warps. Its boundary, known as the magnetopause, begins to flutter like a flag in the wind, reacting to even the slightest perturbation. Inside this unstable shell, currents shift chaotically, electric fields build where none should exist. Satellites orbiting in the outer regions of this fluctuating bubble experience rapid swings in radiation levels, sometimes hundreds of times stronger than normal. In extreme cases, these swings can disrupt communications, damage electronics, or knock spacecraft offline altogether. But the disturbances aren't confined to orbit. Down below, the Earth feels it too. When the magnetosphere flexes and stretches, it changes how energy flows between the planet and space. Electric currents that normally circle high in the ionosphere can suddenly dive lower, bleeding into the atmosphere and even into the ground. These telluric currents, invisible yet potent, have been recorded rising by orders of magnitude during vacuum events. Power grids hum with excess voltage. Pipelines act as unintended conductors, and in regions of high conductivity where the crust is saturated with minerals, salt water, or magma, those currents can run deep. The vacuum effect doesn't strike with the drama of a solar flare. It creeps in quietly, changing invisible forces that few humans ever think about. Yet, for those who study space weather, it represents one of the most mysterious and least predictable aspects of the Sun-Earth connection. Because when the solar wind density collapses, the rules of interaction between our planet and the cosmos change completely. To visualize it, imagine the solar wind as a river flowing steadily past a boulder, Earth's magnetic field. Under normal conditions, that river presses against the boulder, shaping smooth eddies downstream. But if the river suddenly drains away, the boulder's influence expands, turbulence increases. The eddies become chaotic, swirling in unpredictable directions. The absence of water doesn't bring calm, it brings instability. The same is true for space. When the solar wind thins, the magnetic balance that keeps Earth's environment stable begins to fray, and that instability may reach deeper than anyone expected. In the weeks after the September storm, ground sensors across the world picked up strange readings. Subtle oscillations appeared in magnetelluric data, tiny rhythmic pulses in the Earth's magnetic field that didn't correspond to known solar activity. These pulses were global, not local. They rippled through continents like invisible tides, faint but unmistakable. Some scientists theorized they were caused by interactions between the expanding magnetosphere and the weakened solar wind, essentially the planet ringing as it adjusted to new external conditions. But others proposed a bolder idea. The vacuum itself might be transferring energy inward. In classical physics, space is a void, but in plasma physics, emptiness can be active. A sudden drop in particle density creates a pressure gradient, and nature abhors gradients. To restore balance, energy flows from regions of high pressure to low, often in unpredictable ways. When the vacuum formed around Earth, that imbalance extended across the magnetosphere, driving currents along field lines that plunged toward the poles. These currents, in turn, compressed the ionosphere, generating electric fields that reached the planet's surface. In effect, the vacuum created its own invisible storm, a storm not of particles, but of absence. And the more scientists examined it, the more it seemed that this empty space was anything but empty. The Parker Solar Probe recorded something never seen before: micro-scale magnetic vortices, forming within the low-density region near Earth's orbit. They appeared spontaneously, like whirlpools in water, twisting and dissipating in seconds. Their formation suggested that even when particle density is low, the magnetic energy of space remains active, searching for equilibrium. These vortices released bursts of energy known as Alven waves, which propagated along magnetic field lines like ripples in a string. When they reached Earth, they induced low-frequency oscillations that matched the mysterious pulses seen in ground data. It was a feedback loop, space responding to its own emptiness. But if these waves could reach the ground, what else could they affect? That question became more urgent when a cluster of minor seismic tremors began along the Pacific Ring of Fire, almost perfectly aligned with the timing of the vacuum's peak. None of the quakes were catastrophic, but they occurred in regions already stressed by earlier activity. To some researchers, it looks suspiciously like the Kamchatka event all over again, only smaller, distributed, and synchronized. Could the vacuum effect be nudging Earth's crust just as solar storms seemed to? The mainstream consensus said no, but the data refused to sit quietly. Patterns kept appearing: electromagnetic fluctuations preceding tremors, pressure variations in the ionosphere coinciding with shifts in ground conductivity, even faint, measurable correlations between solar wind density and microseismic noise. These weren't coincidences, they were signals of interaction. To those who believed in the interconnectedness of all things, the so-called electric universe school, this was confirmation. They saw the heliosphere not as a passive field, but as a living network of energy exchanges. The vacuum wasn't a gap. It was a reconfiguration, a moment when the cosmic current rewrote itself. In their view, space doesn't just influence planets, it breathes through them. When the solar wind slows, the planet inhales. When it surges, the planet exhales. The vacuum then was Earth's deep breath in. The poetic notion wasn't entirely unfounded. Data from the European Space Agency's solar orbiter confirmed that during the low-density period, the orientation of the interplanetary magnetic field flipped twice in less than 24 hours. Normally such reversals are rare, but within a vacuum, magnetic field lines can reconnect more freely, snapping and reforming like the tendrils of a jellyfish. Each reconnection releases bursts of energy, sending shockwaves across millions of kilometers. These waves can compress or expand the magnetospheres of planets, creating ripples that propagate through space and time. In other words, the vacuum effect was more than an absence. It was an amplifier. It magnified whatever forces were already in motion, taking small fluctuations and stretching them into large-scale disturbances. When combined with the chaotic electromagnetic field of the interstellar comet 3IATLAS, the effect became even stronger. Some models suggested that the comet's plasma tail, now fully extended and ionized by solar radiation, may have acted as a temporary drain on the heliospheric current, pulling energy and particles away from the Sun-Earth system. If true, it would mean that the vacuum wasn't just a solar phenomenon, it was an interstellar one. That possibility sent a chill through the scientific community, because if an external object could alter the density of the solar wind across such vast distances, it meant our solar system's electromagnetic balance was far more fragile than anyone had imagined. The sun might be the heart of the system, but even a passing fragment from beyond could momentarily change its pulse. By early October, the vacuum began to close. The solar wind density crept back toward normal levels, and the magnetosphere contracted to its usual size. But something had changed. The Earth's magnetic resonance frequencies, the subtle oscillations that define its electromagnetic heartbeat, shifted by measurable amounts. The Schumann resonances, normally stable at around 7.83 Hz, showed irregular. Sensitive instruments detected harmonic overtones that had never been observed before. It was as though the planet had been struck like a bell and was still ringing. For most of the world, the event passed unnoticed. Life went on. The news turned to politics, entertainment, and sports. But among the small community of solar physicists and geophysicists who had followed the data, a quiet realization settled in. We had just witnessed something fundamental. The vacuum effect wasn't a glitch or a coincidence. It was a reminder that space and Earth are parts of the same living system, constantly exchanging energy through unseen channels. The emptiness between worlds is not empty at all. It is charged, dynamic, alive. When that vacuum opened around our planet, we caught a glimpse of the universe's hidden architecture, a web of magnetic and electric threads stretching across the solar system. For a few fleeting days, the curtain lifted and we saw how intimately connected everything truly is. The sun, the Earth, the magnetic storms, even the quakes beneath our feet. Then, as quickly as it had come, the vacuum dissolved. The data stabilized, the world forgot, but deep in the archives of observatories and satellites, the signatures remain, a cosmic fingerprint of the moment when space itself breathed in and the Earth listened. Because the silence of that vacuum was not the absence of energy, it was the pause between beats. The universe had drawn its breath, and somewhere out there beyond the reach of our instruments, it was preparing to exhale again. There's a peculiar symmetry in the way the planet behaves. When a massive earthquake strikes one side of the world, subtle tremors sometimes ripple across its exact opposite point, the antipode, as if the Earth itself were a resonant sphere responding to its own vibrations. For centuries, this phenomenon has been a footnote in geophysics, something noted but rarely understood. Yet in the wake of the solar chaos of 2025, that symmetry began to look less like coincidence and more like communication. When the September 18th Kamchatka quake struck, a few observatories around the world caught something unusual. Seismographs in the South Atlantic and the Antarctic Plateau, locations nearly antipodal to the quake's epicenter, recorded faint, low-frequency vibrations. They weren't the typical PNS waves that propagate through the planet after a major seismic event. These signals were stranger, standing waves, reverberations that seemed to pulse at consistent intervals long after the quake's energy should have dissipated. Normally, such readings would be dismissed as echoes, reflections of seismic energy bouncing through the mantle. But these weren't reflections. They were synchronized oscillations, repeating in intervals that didn't match the expected travel times of known seismic modes. It was as though something on the opposite side of the planet had responded, not to the mechanical shaking, but to the timing of the event itself. This became known, informally, as the antipodal mystery. At first, the theory sounded far-fetched. Earthquakes generate waves that travel through rock, not through the air or magnetic fields. The idea that a quake in Kamchatka could somehow talk to the South Atlantic defied the standard model of geophysics. But then researchers looked at the broader context, the timing of the solar storms, the vacuum effect, and the ongoing electromagnetic fluctuations surrounding Earth. And a new possibility emerged. Maybe the planet wasn't responding mechanically at all. Maybe it was responding electromagnetically. To understand how that could happen, it helps to think of Earth not just as a ball of rock, but as a layered electrical system. The outer core is molten iron, spinning and generating the magnetic field that protects the planet. Above that lies the mantle, dense, viscous and full of conductive minerals. At the surface sits the crust, riddled with fault lines and saturated with groundwater and metal ores. Together these layers form a natural circuit, capable of conducting electric currents on a planetary scale. Now imagine what happens when an enormous surge of electromagnetic energy like the one from a geomagnetic storm or solar wind vacuum flows through that system. Those currents don't distribute evenly. They follow paths of least resistance, concentrating along conductive zones such as fault lines. In Kamchatka, that means the subduction zone where the Pacific plate dives beneath the Okhotsk plate, a region that's practically a superconductor for telluric currents. When the September quake struck, it released not just mechanical energy but also electromagnetic energy stored in those stressed rocks. That energy propagated through the crust and mantle, guided by the planet's magnetic field, and when it reached the opposite side of the globe, it induced faint but measurable disturbances in the geomagnetic field there. In other words, the Earth wasn't just shaking, it was sending a signal through itself. If this sounds speculative, it's because it is, but it's also grounded in emerging science. The study of electromagnetic precursors to earthquakes has revealed that rocks under stress can generate electric and magnetic fields through a process called piezoelectricity. When faults are close to failure, those fields intensify. Combined with external electromagnetic forces from space weather, they can create interference patterns that span thousands of kilometers. In Kamchatka's case, the external conditions were extraordinary. The magnetosphere was still expanding, contracting from the solar wind vacuum. The ionosphere above the quake zone had been fluctuating for days. Satellite data showed increased electron density over the region just before the event, an anomaly often seen before major earthquakes. And as if that weren't enough, the planet's electromagnetic environment was already charged by the presence of the interstellar comet 3IATLAS, whose plasma interactions were bending magnetic field lines across millions of kilometers. In short, the stage was set for a global resonance. When the quake released its energy, the entire system Earth magnetosphere, ionosphere, responded like a struck bell. But because the planet's magnetic field isn't symmetrical, that energy didn't distribute evenly. Instead, it focused along specific lines of force magnetic pathways that connected Kamchatka to the South Atlantic and Antarctica. Those regions became the mirror points, the places where the energy converged and rebounded. The antipode wasn't just the opposite side of the globe, it was the other end of an invisible electrical wire. This realization began to reshape how some scientists viewed seismic energy. Traditionally, earthquakes are seen as purely mechanical phenomena, caused by the grinding of tectonic plates. But what if that's only part of the equation? What if the Earth's crust is both mechanical and electrical? A hybrid system where physical stress and electromagnetic charge build together, influence one another, and sometimes trigger each other. Such an idea isn't entirely new. Nikola Tesla once suggested that Earth could conduct electrical resonance on a global scale, capable of transmitting energy instantaneously through its interior. His vision was dismissed as fantasy, but in light of new data, it seems he may have been touching on a deeper truth. The Earth does resonate constantly, and those resonances can be influenced by cosmic forces, from solar storms to geomagnetic vacuums. During the weeks following the Kamchatka event, more anomalies appeared. Instruments at the Amundsen-Scott South Pole Station detected magnetic micropulsations synchronized with fluctuations recorded at Kamchatka's coastal observatories. These pulses weren't random noise, they followed a repeating pattern every 22 minutes, exactly matching the oscillation period of Alfvén waves traveling through Earth's magnetosphere. That timing implied a coupling between the planet's interior and the plasma environment above it, a link spanning from the core to the edge of space. What was even more intriguing was that the amplitude of those signals increased when the solar wind density dropped. In other words, the weaker the external pressure, the stronger the internal resonance. The Earth was louder when space was quieter, a paradox that made perfect sense if the vacuum effect had truly expanded the magnosphere, allowing it to vibrate more freely. Some researchers began referring to this as the planetary echo hypothesis. In their model, major seismic events don't simply release energy, they also tune the planet's electromagnetic field. The release acts like a pluck on a string, setting up oscillations that travel along the field lines to the opposite hemisphere where they either dissipate or reflect back. Over time, these oscillations could influence where stress accumulates next, creating a feedback loop that links seismic zones thousands of kilometers apart. If that's true, then earthquakes might not be isolated events. They could be part of a global network of energy redistribution, mediated by both mechanical and electromagnetic forces. A quake in Kamchatka might relieve pressure there while subtly increasing it in the Andes. A tremor in Chile might months later echo in Japan. The Earth's crust, under constant cosmic bombardment, could behave more like a fluid circuit than a rigid shell. As the data accumulated, the pattern became harder to ignore. The antipodal responses weren't isolated to Kamchatka. Similar phenomena had been recorded after other large quakes in Sumatra, Chile and the Himalayas, but never with such clear electromagnetic correlation. The 2025 events were different because of timing. They occurred during one of the most magnetically unstable periods in recent memory, under the influence of both solar chaos and an interstellar visitor. The result was a perfect laboratory for observing how deeply space and Earth intertwine. And if Earth's magnetic mirror truly reflects energy from one side to another, then the implications extend far beyond geology. It means the planet's entire system, its core, its crust, its atmosphere, is integrated into the cosmic web described in earlier sections. The same electrical currents that connect planets to the Sun may also connect hemispheres to each other, creating a feedback network of unimaginable complexity. To some, this is the ultimate evidence that Earth is not an isolated body, but a living part of the solar symphony. Each quake, each magnetic pulse, each shimmering aurora is a note in that music. The antipodal mystery is the echo, the proof that the melody plays all the way through the planet and back again. By October 2025, that echo had begun to fade. but it left a measurable imprint. The magnetosphere's oscillations gradually returned to baseline, yet subtle anomalies persisted for weeks. Even deep ocean pressure sensors detected tiny rhythmic variations, like the planet's heartbeat taking longer than usual to settle. It wasn't the first time Earth had mirrored its own convulsions, and it won't be the last, but never before had we been able to see it so clearly, in both the physical and the electromagnetic realms. The antipodal mystery remains unsolved, yet its message is unmistakable. When the Earth moves, it doesn't move alone. It resonates with itself, with the sun, and with the endless current of the universe flowing through it. And in that resonance lies a quiet, humbling truth. Every tremor, every spark, every flash of light in the night sky is part of a single, continuous vibration, the heartbeat of a planet that feels everything. By late October 2025, the data no longer looked like noise. The patterns were too consistent, the timing too precise, the interplay between solar, terrestrial, and interstellar events too cleanly aligned. For weeks, scientists had tracked a sequence that began with the sun's awakening, rippled through the Earth's magnetic field, triggered seismic echoes around the world, and seemed to crescendo each time the interstellar comet 3IATLAS passed through another critical point in its orbit. It was a symphony of cosmic energy, and the more they studied it, the harder it became to explain it away as mere coincidence. But where science hesitates, speculation fills the void, and that void was massive. Online forums exploded with theories. Physicists, amateur astronomers, and armchair thinkers all tried to make sense of what was happening. The dominant theory, the one that caught fire across every social media platform, was simple but electrifying. What if 3IATLAS wasn't just a comet? What if it was something else? Something designed, or at least manipulated, by an intelligence beyond our own? It began innocently enough. A group of independent researchers from Eastern Europe, analyzing magnetometer data from the September storm, noticed that the fluctuations in the solar wind during 3IATLAS's closest approach followed a repeating pattern. It wasn't random. Every 7 hours and 42 minutes, there was a slight but measurable dip in particle density, like a pulse. The pattern persisted for almost 3 days before fading. No natural process in cometary physics could account for such periodic precision. Jets of gas don't fire in exact intervals. Outgassing cycles aren't clockwork. When the findings were published in an online preprint archive, mainstream scientists dismissed them as overinterpretation. Instrumental artifact, one reviewer commented. A coincidence amplified by confirmation bias, but the pattern was real, visible in datasets from multiple observatories across the globe. Even NASA's own ACE spacecraft, positioned at the L1 Lagrange point, picked up the same 7-hour modulation in the plasma flow. That's when the whispers began. Some claimed the modulation was a communication signal, a transmission embedded in the solar wind, broadcast by the comet itself. Others suggested it was the byproduct of a propulsion system, an energy source so advanced that we mistook it for natural plasma interaction. A few even speculated that 3IATLAS wasn't a comet at all, but a derelict probe, wrapped in dust and ice after eons of drifting through interstellar space. To be clear, there was no proof of any of this, but the timing of these discoveries, right as Earth's geomagnetic field began showing unexplained anomalies, made it irresistible to the public imagination. Even within scientific circles, there was unease. Something about 3IATLAS defied categorization. Its coma was too large, its electromagnetic influence too strong, and its structural stability, despite violent solar heating, too improbable. Normal comets shed material rapidly as they approached the sun, often breaking apart near perihelion, but Atlas held together. It flexed, dimmed, brightened again, and survived. That resilience alone made it an outlier. Then came the radio anomalies. Deep space listening arrays in Australia and South Africa, tuned to study solar wind scattering, detected faint narrowband signals coinciding with the comet's position. These signals were barely above the noise floor, too weak for ordinary interpretation, but they stood out because of their spectral purity. Natural emissions, like those from solar plasma or cosmic background radiation, spread across wide frequency ranges. They were sharp, distinct, and steady. At first, engineers assumed interference may be reflections from terrestrial sources, or even Starlink satellites, but cross-checks ruled that out. The signal was consistent across multiple stations separated by thousands of kilometers. Whatever it wasn't coming from Earth. The scientific response was cautious. Officially, agencies refused to attribute any artificial origin. But privately, data analysts began exploring unconventional models. Could the signal be a natural resonance created by the interaction between the comet's ionized tail and the heliospheric magnetic field? Maybe. But no simulation fully reproduced its structure. By mid-October, public interest had turned feverish. YouTube channels, podcasts, and news outlets seized on the idea that Earth was witnessing its first verified encounter with an alien object. One that wasn't merely passing by but doing something. The theories ranged from the grandiose to the absurd. Some claimed the comet was seeding the sun with magnetic information, subtly altering its behavior. Others argued it was mapping our solar system using electromagnetic feedback loops. The most extreme voices declared that 3IATLAS was harvesting energy from the sun, a cosmic parasite feeding on stellar plasma. The term energy harvester took hold, spreading like wildfire across the internet. The idea wasn't entirely without basis. The comet's vast coma, half the size of the sun and highly conductive, was acting like a collector, sweeping through the solar wind and gathering charged particles. Theoretically, such a structure could accumulate electrical potential equivalent to billions of volts. If one imagined an advanced species capable of manipulating plasma on that scale, 3IATLAS suddenly looked less like a rock and more like an engineered mechanism. A natural fusion reactor turned into a tool. Of course, mainstream astrophysics stayed grounded. NASA, ESA, and JAXA released statements, emphasizing natural explanations, volatile compounds reacting with sunlight, unpredictable gas jets, plasma interactions amplified by solar conditions. But none of these statements addressed the recurring 7-hour modulation. None explained why the comet's magnetic footprint lingered long after it passed perihelion, or why Earth's magnetosphere continued oscillating in sync with its movement days after it began its outward journey. A small but growing faction of researchers began entertaining a softer version of the alien hypothesis. Not of direct intelligence, but of intelligent origin. What if 3IATLAS was debris, not from nature, but from an extinct civilization, remnants of an ancient technological construct from another star system? A fragment of something once alive, now adrift. That notion carried a strange poetry. If the object truly were an artifact, then the interactions we observed, magnetic modulations, plasma disturbances, and electromagnetic echoes, might be nothing more than relic processes, automated systems performing meaningless cycles long after their creators were gone. In that interpretation, 3IATLAS wasn't visiting us, it was remembering. But even for those unwilling to step into speculation, the practical implications were staggering. Whether natural or artificial, the comet's presence had coincided with a chain of events that altered Earth's entire electromagnetic environment. And if a single interstellar body could have that effect, what did that say about our vulnerability as a planet? As October deepened, researchers noticed something even more bizarre. The modulation in the solar wind that had been associated with 3IATLAS didn't fade completely when the comet began moving away. It simply shifted. The frequency increased slightly, now pulsing every 6 hours instead of 7. Some speculated that the source had moved to a new point of interaction, perhaps deeper within the heliosphere. Others wondered whether the modulation had been absorbed by the solar magnetic field itself, now resonating through it like a sustained vibration. It was as though the sun had learned a new rhythm and was repeating it back. That was when the term solar memory entered the discussion. Plasma physicists know that magnetic fields can store information in the form of configurations, patterns of current and polarity, that persist long after the initiating force disappears. If 3IATLAS had disturbed the sun's magnetic topology, then the resulting oscillations could theoretically persist as standing waves in the heliospheric current sheet. That might explain why the periodic signals continued after the comet's departure. But it also raised a haunting question. Could the sun now be echoing something it had absorbed, some pattern, some data from an external source? By this point, the alien hypothesis had fractured into factions. The conservative camp argued that 3IATLAS was a purely natural object, whose peculiarities simply pushed the limits of current models. The speculative camp insisted it was an engineered remnant. And then there were the radicals, the ones who believed the comet was not merely passing through but intentionally communicating. They pointed to the precision of the modulations, the strange persistence of the signals, the synchronized disturbances across Earth's magnetic field. To them it wasn't random, it was a pattern, a broadcast, a knock on the cosmic door. Most scientists rejected that outright. but quietly a few admitted they couldn't explain everything. The vacuum effect, the antipodal resonances, the global synchronization of magnetospheric fluctuations, all of it formed a tapestry of connections that defied easy dismissal. If 3IATLAS were a messenger, its message remained indecipherable, yet its arrival had already changed humanity, not through words but through awareness. It reminded us how fragile our understanding truly is. We look to the heavens and think we know the rules, but every so often the universe sends something to remind us how little we actually see. Whether natural wonder or alien relic, 3IATLAS had done what no spacecraft or discovery could. It forced the world to confront the possibility that the cosmos isn't indifferent, it's interactive, and perhaps, just perhaps, it's listening. If it was a message, it wasn't meant for just one species, or even one planet. It was a pulse in the magnetic web, a ripple in the universal current, echoing through space and time, a reminder that intelligence might not always come with language or life as we know it. Sometimes intelligence arrives as a pattern, as a frequency, as a resonance that makes an entire planet quiver, look up, and wonder whether the universe has just whispered its first word. By the beginning of November 2025, the world's observatories, satellites and research stations were awash with data, terabytes of numbers, waveforms and electromagnetic maps that spanned from the edge of the heliosphere to the molten heart of Earth. What had started as a series of disconnected anomalies, solar storms, seismic surges, magnetic distortions, and the haunting passage of the interstellar comet 3IATLAS, had now coalesced into something undeniable, a pattern too persistent to ignore. Yet what that pattern meant, no one could agree on. In laboratories from Geneva to Tokyo, the most powerful computers ever built churned day and night, searching for relationships between variables that refused to behave. Supercomputers plotted correlations between solar wind speed and seismic activity. Artificial intelligence systems were trained to detect periodicities in magnetospheric oscillations. Algorithms compared the timing of auroral flares, atmospheric density changes, and ionospheric discharges. The deeper they dug, the more interlaced the phenomena became, as though every element of the Sun-Earth system were moving to the same hidden rhythm. At NASA's Goddard Space Flight Center, a team of plasma physicists pored over readings from the Parker Solar Probe. In the weeks following 3IATLAS's closest approach, the spacecraft had recorded subtle changes in the solar magnetic field, tiny but consistent rotations in field direction, occurring at intervals that echoed the comet's peculiar 7-hour modulation. At first they assumed instrumental drift, but when the same signature appeared in data from the Solar Orbiter and even from Voyager 2, still drifting through interstellar space billions of kilometers away, the coincidence turned into a puzzle. Whatever had happened in the heliosphere, it had rippled outward. Meanwhile, on Earth something equally strange was unfolding. Magnetometers in multiple hemispheres began detecting a low-frequency vibration that seemed to pulse through the planet's magnetic field like a global heartbeat. It wasn't seismic, it wasn't atmospheric, and it wasn't human-made. It came in cycles, slow, deliberate, persistent. The signal was weak but global, appearing simultaneously in stations across Asia, Europe, and South America. Some called it the resonance. Others, with a mix of awe and unease, began calling it the Atlas signature. The first to recognize its potential significance was a quiet group of researchers at the European Space Agency's Space Weather Analysis Division. While reviewing cross-correlations between ground magnetometers and satellite readings, they noticed that the frequency of the Atlas signature aligned almost perfectly with shifts in solar wind velocity recorded weeks earlier. The implication was staggering. Earth was still vibrating to the echo of a cosmic event that had already passed. If true, it meant the planet itself had recorded the encounter. To test the theory, the team began constructing what they called a planetary coherence model. It was an attempt to map how external electromagnetic energy originating from the Sun or even from interstellar space propagates through the Earth's coupled systems, the magnetosphere, the ionosphere, the crust, and the oceans. Using historical data from past solar cycles, they discovered faint but recurring harmonics resonances that repeated every 11 years, corresponding with the Sun's polarity reversals. But the 2025 data didn't fit those cycles. The harmonics were new, they were sharper, cleaner, more organized. The model suggested that a standing wave might have formed across the heliosphere itself, a massive planet-spanning resonance linking the Sun, Earth, and possibly the passing comet. If that were true, It would mark the first evidence that the solar system could sustain long-lived electromagnetic memory. When the findings reached the United Nations Office for Outer Space Affairs, they were quietly filed under ongoing research. Publicly, no one wanted to fuel another wave of speculation. Privately, the scientists involved couldn't stop talking about it, because buried in those harmonics, hidden among the chaos of magnetic data, was a repeating sequence that seemed almost deliberate, a mathematical progression too orderly for random turbulence. It was a sequence of ratios: 1.6118, 2.7118, 3.145. The golden ratio, Euler's number, and at first the pattern looked like a statistical mirage, but the more datasets they cross-referenced, solar plasma densities, auroral frequencies, magnetospheric pulses, the clearer the ratios became. They weren't exact numbers, but approximations that converged within tiny margins of error. Nature, of course, contains those constants everywhere, in spiral galaxies, in seashells, in the structure of storms. But to find them embedded in the timing of electromagnetic waves, spanning millions of kilometers, it felt less like coincidence and more like design. Even the skeptics were unsettled. At the International Geophysical Union's Emergency Symposium that month, researchers debated the findings in tense sessions that ran deep into the night. The question wasn't whether the data were real, they were, but what they represented. Were these natural harmonics emerging from nonlinear feedback within the Sun-Earth system? Or were they the lingering fingerprints of something external? Perhaps 3IATLAS itself imprinting a mathematical resonance on the magnetic fields it disturbed. Dr. Annika D'Souza, a geophysicist from Mumbai University, presented a provocative hypothesis. She argued that the entire solar system acts as a plasma memory array, a structure capable of storing information in its electromagnetic topology. When a powerful external field, such as that generated by 3IATLAS, interacts with the Sun, it can reconfigure the magnetic geometry of the heliosphere, encoding data in standing waves that persist long after the event. In her words, "Space remembers." Her presentation was met with silence, then with cautious applause. Meanwhile, other scientists pursued a different mystery. Deep within the Arctic Circle, the EISCAT radar facility had been monitoring the ionosphere during the October events. Reviewing their logs, they discovered something they had never seen before: a sudden symmetrical enhancement in electron density across both hemispheres, separated by exactly 12 hours. It was as if the planet's upper atmosphere had conducted a signal from one pole to the other, bouncing it back in perfect timing. The symmetry was unnerving. It hinted at a coordination between hemispheres that no known natural process could produce spontaneously. If the Earth's atmosphere had acted as an antenna, what then was it receiving? At CERN, physicists began looking for correlations between the solar anomalies and variations in cosmic ray flux. To their astonishment, the flux data showed dips corresponding precisely with the periods of geomagnetic resonance. Cosmic rays, high-energy particles from beyond the galaxy, were being deflected in synchronized bursts. The implication: the magnetic shield around Earth wasn't just reacting, it was modulating, as if tuned by an external hand. Taken together, the findings painted a picture that was almost mythic: a solar system alive with structure, responding to patterns too coherent for randomness. By mid-November, governments began to take notice. Private briefings circulated between agencies. NASA, ESA, and Roscosmos formed a joint task force called HELIOS, Heliospheric Electromagnetic Interaction Observation System. Their mandate was simple but monumental: determine whether the observed harmonics represented natural plasma dynamics or intelligent design. Officially, the mission would be described as an investigation into heliospheric coherence. Unofficially, it was an attempt to answer the question everyone had been asking in whispers: did something touch the Sun? Helios pulled data from every available source: the Solar Dynamics Observatory, the Deep Space Network, magnetometers aboard commercial satellites, even declassified military sensors. The analysis ran 24 hours a day for weeks, each team specializing in a single variable: magnetic flux, solar wind density, spectral emissions. When the results finally emerged, they revealed something astonishing. Across all datasets, one constant appeared: a recurring oscillation at precisely 0.039 Hz, roughly one cycle every 25.6 seconds. It was faint but persistent, detectable from the solar corona all the way down to the Earth's ionosphere. No known solar or planetary mechanism operates at that frequency. Yet it was there, steady as a heartbeat, resonating through every layer of the system. To the Helios team, it became known as the pulse. The pulse was unlike anything recorded before. It wasn't electromagnetic noise, nor was it seismic in origin. It was coherent, a global standing wave that seemed to modulate energy flows between the Sun and Earth. The team's working hypothesis suggested that during 3IATLAS's passage, its immense plasma tail might have temporarily bridged regions of the heliosphere, creating a channel for magnetic resonance to propagate directly between star and planet. When the comet moved on, that resonance didn't vanish. It stabilized into a persistent oscillation. In essence, the Sun and Earth were still connected, still talking long after the event. Some on the team saw the implications as benign, even wondrous. They imagined new frontiers in physics, a chance to study cosmic coupling at an unprecedented scale, to unlock the hidden architecture of solar planetary systems. But others were less sanguine. If an external object could alter the electromagnetic behavior of an entire star system, even temporarily, what would happen when another such object arrived? One larger, more charged, or moving in a more destructive path? For the first time, humanity had empirical evidence that the cosmos could interact with us in ways we had never anticipated. Outside the closed circles of science, conspiracy theories multiplied. Some claimed the pulse was a message. Others said it was a warning. A few saw it as the activation of a long-dormant mechanism buried in the solar system since its formation. Theories flourished faster than facts could catch up. Yet beneath the noise, one undeniable truth persisted. Something had changed in the fabric of our solar environment, and the data proved it. By December, the pulse was still measurable, though weaker. It faded slowly, like the last echo of a bell ringing through the void. But before it disappeared entirely, it left one final gift, a global synchronization event. For a brief 20-minute window on December 3rd, magnetometers around the world recorded identical fluctuations, perfectly aligned to within fractions of a second. It was as if the entire planet had inhaled and exhaled together, one unified breath in the electromagnetic web. No one could explain it. No one could deny it. The data remain archived today, petabytes of raw information that may take decades to decode. But among the scientists who lived through those months, one conviction endures. We witnessed something that rewrote the boundary between Earth and cosmos. Sun is no longer just our star, it's our partner in an ongoing dialogue, one that transcends distance, language, and time. And if the data truly hold the signature of another intelligence, whether born of physics or purpose, then 2025 will be remembered not for the storms or the quakes, but for the moment humanity realized the universe itself might be conscious enough to speak. We had always watched the heavens, searching for signs of life, but perhaps life had been speaking all along, not in radio waves or lights in the sky, but in the silent, rhythmic data of the cosmos, a pulse that binds the sun, the earth, and everything between in a single shared vibration. There are moments in history when everything seems to align, not just metaphorically, but literally. October 2025 was one of those moments. The term the October Nexus, as coined later by the Helios research team, a phrase that tried to capture what had happened during that month when cosmic forces, planetary movements, and human awareness seemed to merge into one coherent event. But at the time, no one truly understood what they were witnessing. All anyone could agree on was that the world had entered a strange kind of synchrony, a period where every system from the sun's corona to the Earth's molten core seemed to be pulsing to the same invisible rhythm. In early October, as the interstellar comet 3IATLAS passed its perihelion, the sun flared again. It wasn't the most powerful flare in history, not even close. But what made it unusual was its precision. The X-class eruption erupted from the sun's equator almost exactly as the comet crossed the same heliographic latitude. To astronomers, this was simply geometry, a line-of-sight coincidence. But when the flare's electromagnetic shockwave reached Earth 14 hours later, something unprecedented occurred. Instead of dispersing chaotically through the magnetosphere, the incoming waves split cleanly into hemispheric harmonics. Northern and southern auroras ignited simultaneously, mirror images of one another, dancing in identical patterns from Alaska to Tasmania. Even seasoned scientists found themselves transfixed by the symmetry. Satellite imagery revealed the auroras forming concentric spirals, rotating in opposite directions, yet maintaining perfect mathematical balance. as if the planet were caught in the middle of a cosmic tug-of-war, suspended between equal and opposite forces. It was beautiful, it was terrifying, and it was just the beginning. For days afterward, Earth's entire electromagnetic environment hummed with subtle oscillations. Power grids across Europe and North America reported fluctuating current frequencies. Pilots described compass needles twitching erratically mid-flight. Amateur radio operators picked up ghost signals echoing across multiple bands, fragments of strange tones repeating in rhythmic intervals. These signals, when analyzed, matched the same 0.039 Hz pulse that had appeared in the solar data weeks before. Whatever the pulse was, it had fully synchronized with Earth by then. Helios scientists called it coherence locking. In plain terms, it meant the Sun and Earth were oscillating together in resonance, like two tuning forks vibrating in harmony. The energy exchange between them had reached a point of feedback, where each reinforced the other. Theoretically, such a condition should have been impossible. The Sun's plasma environment and Earth's magnetosphere operate on vastly different scales, separated by millions of kilometers of space. Yet somehow the energy patterns bridged that gap seamlessly, creating a temporary circuit that linked both bodies as though they were parts of the same living machine. The effect wasn't purely electromagnetic. Atmospheric scientists began noticing anomalies in global pressure systems. Jet streams shifted unpredictably, bending and twisting in strange loop. Cloud formations appeared in geometric shapes, hexagonal, spiral, and linear, mirroring patterns usually seen only in polar vortexes. In the oceans, subtle fluctuations in surface temperatures appeared across the Pacific and Indian basins, following the same periodic timing as the pulse. Even animal behavior seemed to reflect the change. Whales in the southern hemisphere began altering their migration routes. Schools of fish surfaced at unusual depths, and birds deviated from their seasonal paths by thousands of kilometers. For those paying attention, it was as if the entire biosphere was moving to an unseen metronome. In the scientific community, this alignment was met with both awe and dread. The idea of a planetary coherence event was no longer theoretical. It was measurable. Every branch of Earth science was detecting it in some form. Seismologists observed harmonic tremors in volcanic zones that matched the same frequency as solar data. Climatologists found synchronization between upper atmospheric pressure waves and magnetic field oscillation. Even biologists began recording subtle changes in circadian rhythms among plants and animals, suggesting that life itself was responding to the same underlying signal. The October nexus had become more than a cosmic curiosity. It was transforming the planet's equilibrium. By mid-October, the resonance reached its peak. Helios satellites recorded a burst of electromagnetic coherence that enveloped the entire magnetosphere, temporarily stabilizing it into an almost perfect spherical symmetry. For 43 minutes, Earth's magnetic field pulsed in unison. No turbulence, no irregularities, no drift. It was as though the planet had achieved a brief state of electromagnetic perfection. The world's power systems, oddly enough, ran smoother than ever during that window. Voltage fluctuations dropped to zero. Communication satellites operated without interference. Even GPS accuracy improved beyond normal tolerances. It was as if nature itself had synchronized with technology. But as the coherence faded, new disturbances followed. When the magnetic symmetry collapsed, the stored energy released unevenly, causing what the Helios team later called a magnetoelastic rebound. In plain terms, the Earth's field snapped back into its usual chaotic shape, but with a twist. The poles shifted slightly, not geographically but magnetically. North and south both moved by a fraction of a degree, enough to register on sensitive instruments. It was a subtle change, invisible to most, but to those studying geomagnetism, it was monumental. That tiny movement carried profound implications. The magnetic field had realigned itself, almost as if in response to an external push. Some speculated that this was a natural correction, a kind of magnetic aftershock. Others, however, believed it was the direct result of the heliospheric resonance with 3IATLAS, a lingering signature of its passage through the Sun-Earth system. Whatever the cause, the alignment had consequences. The auroral zones expanded, creeping closer to the equator than ever before. In cities like Madrid, Tokyo, and Denver, people looked up and saw colors they had only ever seen in photographs. Red veils, green curtains, violet halos swirling silently across the stars. It was mesmerizing, almost sacred. Many cultures interpreted it as an omen. Social media erupted with awe and fear in equal measure. Videos of the sky went viral under hashtags like Nexus Light and Sky Pulse. Some saw beauty, others saw prophecy. Religious groups declared it the awakening of Earth's consciousness. Skeptics dismissed it as electromagnetic coincidence. Yet even the skeptics couldn't explain why the phenomenon was so precise, why it appeared across both hemispheres at exactly the same time, or why instruments still registered the pulse long after the auroras had faded. And then, almost without warning, everything went quiet. On October 27th, the magnetosphere flattened. Solar wind readings dropped to near zero for nearly 6 hours. The planet entered a period of magnetic stillness so profound that some instruments reported null readings. No measurable fluctuation whatsoever. This had never been recorded before. Space weather networks around the world scrambled to confirm their instruments were still functioning. They were. The Earth's magnetic field had gone still. For 6 hours the planet seemed to hold its breath. Seismographs recorded an eerie calm. Global microseismic noise decreased by nearly 40%. Oceanic turbulence slowed. Atmospheric electricity dipped to record lows. Even lightning strikes decreased dramatically. To those monitoring the situation, it felt as though the entire planet had entered a temporary state of suspension. And then, just as suddenly as it had stopped, the data surged back to life. When the magnetic field resumed, it did so with a new pattern. The familiar 0.039 Hz pulse was still there, but layered on top of it was a higher frequency modulation, sharp, rhythmic, deliberate. At first it was dismissed as instrumental noise, but when 3 separate observatories across different continents detected the exact same pattern, synchronized to within milliseconds, it became clear this was something else. The pulse had evolved. Unlike the slow, deep hum that had defined the earlier resonance, this new modulation was faster, complex, structured, almost musical. When translated into audio frequencies, it produced a pattern of tones that some researchers described as hauntingly odd, not random bursts, but intervals and harmonics, ascending, descending, repeating in fractal sequences. The resemblance to a mathematical signal was unmistakable. Theories abounded. Some believed the new modulation represented the solar system returning to balance, a natural oscillatory correction after the massive energy exchange of the past months. Others whispered darker ideas that the Sun and Earth had become permanently coupled through some unknown mechanism, forming a resonant system that might change how energy flows between them forever. Among the helioscientists, however, one interpretation began to dominate. Dr. Paolo Ferrante, a plasma physicist from the Italian Space Agency, proposed that what they were witnessing wasn't a natural resonance at all, but the stabilization of an artificial structure in space. According to Ferrante, 3IATLAS's plasma interactions could have induced the formation of a self-sustaining electromagnetic lattice between the Sun and Earth, a kind of temporary bridge made of magnetic flux and charged particles. In his view, this bridge might still be echoing, long after the comet had moved on, carrying the memory of its presence in the form of organized oscillations. He called it the nexus field. If Ferrante was right, the October nexus wasn't merely a coincidence of celestial alignment. It was a transformation, a moment when the Sun-Earth system became aware of itself, resonating as one entity for the first time. For the next several days, instruments continued to detect faint traces of the higher frequency modulation. Then, as November dawned, the signal slowly decayed. The skies returned to normal. The auroras faded. The magnetosphere resumed its usual restless fluctuations. The world once again appeared ordinary. But the data remained, a silent record of the moment when the solar system's 2 greatest bodies shared a rhythm. Somewhere in the archives of Helios, buried within endless spreadsheets of numbers, the patterns of the October nexus are still preserved. The synchronized flares, the mirrored auroras, the 6-hour silence, the final harmonic surge, and perhaps if one were to play them back like a piece of music, they would hear what a few scientists dared to whisper even then, that for one fleeting month, Earth and Sun sang the same song. When the last flicker of the October auroras faded into the black sky, the world seemed to exhale. The headlines slowed. The public turned its attention back to politics, sports, and celebrity gossip. The sense of cosmic tension that had held the planet captive for months slowly dissolved into the background noise of ordinary life. But for the scientists, engineers, and silent observers who had followed every pulse, every flicker of magnetism, every seismic whisper beneath the crust. Nothing was the same. The data they had collected didn't vanish with the lights in the sky. It remained, whispering from hard drives encoded in plasma models and frequency maps, hinting that something enormous had changed, and that the Earth might never again return to its former rhythm. The Helios team, once operating in urgency, now found itself in quiet disbelief. They had expected the resonance to fade after the comet 3IATLAS passed beyond the orbit of Mars. Instead, subtle harmonics continued to appear in nearly every magnetospheric dataset. At first, these readings were faint, like echoes of a song heard through water. Then, toward the end of November, they grew stronger, steady, persistent, coherent. The pulse was still alive, and although its intensity had diminished, its structure had evolved. The pattern was smoother now, less erratic, as though the solar system had settled into a new equilibrium. The question no one wanted to ask was simple. Equilibrium with what? Physicists offered natural explanations, each more complex than the last. Some proposed that the events of 2025 had triggered a long-term resonance between the Sun's inner magnetic layers and the outer planets. Others argued that Earth's core dynamics might have been subtly altered by the electromagnetic surges, changing the way it interacted with the heliosphere. A few even speculated that the interstellar object had deposited charged dust or plasma particles that continued to influence solar behavior long after it departed, but none of these theories fully explained the persistence or the precision of the ongoing frequencies. When the Helios data was finally made public in early 2026, independent analysts began poring over the numbers. A small research group at the University of Kyoto noticed something remarkable: the lingering pulse, now oscillating around 0.0389 Hz, had synchronized with a natural resonance of the Earth's own Schumann frequencies. It was as if the heartbeat of the planet had been slightly retuned. Normally, Schumann resonances, the electromagnetic waves trapped between the Earth's surface and ionosphere, exist in distinct modes. The fundamental tone hovers around 7.83 Hz, a constant hum driven by lightning discharges around the world. But now, subtle shifts were appearing in the higher modes, ripples that aligned almost perfectly with the frequencies once traced back to the solar disturbances. To most people, these were numbers on a graph. To those who understood the implications, it was breathtaking. The entire electromagnetic ecosystem of the planet, the invisible symphony of frequencies that connects sky, land, and life had changed, and life, in small and mysterious ways, was beginning to change with it. Biologists in Sweden and Canada began documenting anomalies in animal navigation. Migratory birds altered their routes, veering westward where they had once flown north. Whales began surfacing in unusual locations, drawn off course by invisible signals. Even bees, creatures exquisitely attuned to the planet's electromagnetic field, showed signs of confusion, abandoning hives and resettling miles away. The phenomenon wasn't catastrophic, but it was consistent. Nature was adjusting to a new beat. Human technology, too, seemed to respond to the shift. Engineers monitoring satellite communications noted a curious improvement in signal stability during certain hours, precisely when the resonance amplitude peaked. Atmospheric noise levels, normally a constant irritant for low-frequency transmissions, dropped by measurable amounts. Even global positioning systems, notorious for drift and interference, briefly achieved levels of accuracy never before recorded. The effect was subtle but widespread, a quiet optimization that no software update could explain. Some scientists speculated that the entire solar terrestrial circuit had reached a new kind of coherence, a phase alignment between the Sun's electromagnetic output and the Earth's magnetosphere that reduced interference and increased systemic efficiency. Others dismissed this as poetic overreach, but the numbers were stubborn. In the months following the October nexus, the planet's background magnetic turbulence fell by nearly 8%. The Earth, it seemed, had calmed. But calm in nature is rarely permanent. By January 2026, deep space telescopes began tracking faint disturbances along the heliospheric boundary. They weren't visual, but electromagnetic fluctuations in the magnetic sheath that separates our solar system from interstellar space. Normally, this heliopause moves gently, expanding and contracting with the Sun's activity. But now it was oscillating in rhythm with the same frequency observed in the residual pulse. To put it simply, the entire solar system from the inner planets to its outermost magnetic border was pulsing together. The implications were staggering. If this synchronization continued, it might alter how cosmic radiation entered the solar system, how the solar wind distributed itself, even how planetary magnetic fields evolved. Some speculated that we were witnessing the beginning of a new solar cycle unlike any before, a cycle not purely dictated by the sun, but by the combined resonance of the sun, Earth, and perhaps something else. That something else remained the great mystery. 3IATLAS, now months beyond Mars's orbit, and heading toward the outer solar system, continued to defy expectations. Instead of fading into obscurity like most comets, it remained bright, too bright. Its coma expanded again in mid-December. Despite moving farther from the sun, spectroscopic analysis revealed unusual emission lines, suggesting that the object's interior might be generating energy, not merely reflecting it. Whatever it was not dead. Theories proliferated. Some saw the comet as a natural plasma capacitor, releasing stored energy accumulated during its perihelion encounter. Others suggested that it was still interacting with the sun's magnetic field, acting as a moving node in a larger electromagnetic circuit. But a quiet minority, those who still whispered of intelligent design, offered a more radical idea that 3IATLAS had ignited something within the solar system, a reaction that would continue long after it was gone. Among them was Dr. D'Souza, the same physicist who had introduced the idea of plasma memory to the Helios Symposium. In her final paper before withdrawing from public research, she wrote, "The heliosphere behaves not as a passive environment, but as a resonant organism. When perturbed, it learns. The patterns of 2025 are still echoing because the system is retaining the imprint of interaction. What we are witnessing may not be an event. It may be an awakening." Her words circulated quietly through academic networks, shared more as rumor than as theory. Yet they resonated deeply with those who had watched the data unfold in real time. The idea that space could remember was no longer science fiction. It was consistent with everything the instruments had recorded. But what does a memory mean to a system as vast as the solar system? What happens when the medium of space itself retains a pattern, a rhythm, a signal? Does it simply fade, or does it evolve, seeking new ways to express itself through the structures it connects? In the early months of 2026, a strange form of alignment began to recur. Planetary conjunctions, normally random and widely spaced, seemed to follow the timing of the residual pulse. Mercury and Venus crossed heliographic longitudes precisely aligned with Earth's orbital plane. Jupiter's magnetosphere flared unexpectedly, creating auroras brighter than any seen in decades. Even Saturn's ring system displayed temporary distortions, waves propagating across the icy bands in a way that suggested magnetic interference. It was as if the entire solar system were whispering the same rhythm back and forth, testing its own coherence, and beneath it all, Earth continued to hum. Seismometers detected low-frequency vibrations that defied seismic origin. Atmospheric sensors picked up periodic fluctuations in static potential. Lightning patterns shifted toward more frequent but less intense discharges, as though the planet were bleeding off energy in smaller, rhythmic increments. Adiviv pointed to a new equilibrium, delicate, dynamic, alive. For the first time in recorded history, humans had the data to see themselves as part of that living system, not separate observers, but participants. The boundary between cosmic and terrestrial had blurred. Every breath of solar wind, every flicker of magnetic field, every pulse of light from the sun was part of the same conversation. And yet, with understanding came unease, because no one knew whether this new coherence was stable or temporary, whether it marked the dawn of a new age of cosmic harmony, or the calm before a deeper, more dangerous transformation. The unknown ahead was vast. Some predicted the resonance would fade, its energy dispersing naturally as the sun entered the quieter phase of its cycle. Others feared feedback, that the continued oscillation might amplify until it destabilized the magnetosphere, triggering climatic or seismic repercussions. But there was another possibility, one that a few dared to voice aloud, that the resonance would persist, subtly influencing the evolution of both Earth and humanity. Perhaps we had been altered by it already. The pulse had touched everything: magnetism, biology, technology, even thought. People spoke, quietly, of feeling different during those months, more attuned, more aware, as though their own inner rhythms had synchronized with the heartbeat of the planet. Meditation groups described collective experiences of calm and clarity. Artists created works that mirrored the oscillating patterns of light and sound. Scientists reported bursts of creative insight that led to breakthroughs across disciplines. Was it coincidence, suggestion, or something deeper? No one could say. But one thing was certain. Once the planet had heard the pulse, it could never truly forget it. Even now, years later, long after the comet's light faded beyond the reach of telescopes, the world still carries its echo in the silence between radio static, in the shimmer of auroras, in the measured hum of the Earth's magnetic field. There lingers a rhythm, a reminder of the moment when humanity stood at the edge of understanding and glimpsed for a heartbeat the unity of all things. The October nexus had ended, the vacuum had closed, the data had been archived. Yet something continues to breathe beneath it all, an awareness vast enough to encompass stars, subtle enough to vibrate within atoms, and patient enough to wait for us to notice again. The unknown ahead is not empty. It's listening. When history looks back on the autumn of 2025, it won't remember it for a single event, a disaster or a discovery. It will remember it as a feeling, a subtle but unmistakable sense that the world had changed its rhythm. For most people, the lights in the sky and the tremors in the ground were passing curiosities, brief moments of wonder before the next news cycle took over. But for those who studied the data, for those who listened closely, it was as if reality itself had drawn a slow, deliberate breath, and when it exhaled, the air of the universe carried a different tone. The scientists never reached full agreement on what had happened. Some saw it as the culmination of rare cosmic coincidences, a hyperactive sun, a volatile Earth, and an interstellar comet arriving at precisely the right moment to stir the system's electromagnetic soup. Others believed it was proof of something larger, that the universe operates not as a collection of separate events, but as one continuous field of interaction. To them, the pulse wasn't an anomaly at all. It was a glimpse into the underlying order of things, a reminder that every magnetic ripple, every earthquake, every flicker of light is part of one endless current connecting all matter across space and time. What remained undeniable was that Earth had felt it. The resonance that linked sun, planet, and comet left a measurable imprint, a shift in magnetic frequencies, a new balance in the Schumann resonances, a subtle change in the energy distribution of the upper atmosphere. Those patterns still echo faintly today, buried within the background noise of the planet's natural hum. The pulse may have faded from public consciousness, but it still lives quietly in the numbers, in the silent rhythm of our magnetic field, in the synchronized breath of oceans and storms. Yet perhaps the most profound effect wasn't physical at all. It was psychological. For the first time in generations, humanity was forced to consider its place within a living cosmos. The idea that our planet could resonate with the sun, that cosmic forces could alter the heartbeat of the Earth, reshaped how people thought about existence itself. The separation between space out there and life down here blurred. We began to see ourselves not as inhabitants of a passive world, but as participants in a grand, ongoing conversation between energy and consciousness. The helioscientists called it systemic coherence. Poets called it awakening. Whatever name it carried, the meaning was the same. Something vast had spoken, and the Earth had listened. Whether the voice belonged to a comet, a cosmic mechanism, or the universe itself, no one could say. But it had reached us in the language of frequency, a language older than words, older than stars. And perhaps that's the most humbling part of all, that the universe in its quiet precision doesn't shout. It hums, it breathes, it pulses. And if you're still enough, patient enough, you can feel it, running beneath your feet, whispering in the wind, flickering in the edges of the night sky. The October nexus, the pulse, the so-called solar memory, these are names we gave to something we barely understand. But maybe understanding isn't the point. Maybe the purpose of the unknown is to remind us that discovery is never finished, that wonder still exists, and that our world is still capable of mystery. Because in the end, what truly changed in 2025 wasn't the sun or the earth, it was us. We began to listen differently. We began to notice the quiet harmonies that had always been there, and in that realization, humanity stepped closer to what it has always sought: connection. The silence that followed the pulse wasn't emptiness. It was anticipation, a stillness that comes after a note, waiting for the next to rise. Somewhere out there in the uncharted dark between stars, that rhythm continues. It will return someday, as all cycles do, and when it does, maybe this time we'll be ready to hear the full melody of the universe. a song that was never meant to end, only to remind us that we were part of it all along.